Butter is built on simple ingredients that transform through powerful mechanical precision. From churning high-fat cream into silky butter, to concentrating sweetened milk into a dense golden syrup, each step reveals a different kind of controlled chemistry. Today, we follow every stage of butter, condensed milk, and mozzarella creation to uncover the hidden forces and techniques that turn raw dairy into iconic foods. The butter production process begins with the delivery of raw whole milk to the dairy processing facility, where it enters a separation stage. In this step, the milk is pumped into a centrifugal cream separator, a high-speed spinning drum that divides the milk into cream and skim milk using differences in density. The separator operates at thousands of revolutions per minute, and the heavy skim milk is forced outward, while the lighter cream is pushed inward and directed into a separate channel. This cream is then cooled and stored in refrigerated stainless steel silos, where it is held under continuous agitation to prevent fat separation or layering. Once the cream has reached the correct fat concentration, typically between 35% and 42%, it undergoes pasteurization. In the pasteurization unit, cream is pumped through a heat exchanger where it is rapidly heated to around 85 degrees Celsius and held for a set duration, usually 15 to 30 seconds, before being cooled back down to below 10 degrees Celsius. This step eliminates harmful microorganisms and also slightly modifies the protein structure, which improves the efficiency and stability of churning later in the process. After pasteurization, the cream is sent into aging tanks. These are jacketed stainless steel vessels where the cream rests for several hours at chilled temperatures, often around 5 degrees Celsius. This aging allows the fat crystals to partially form, which improves the eventual butter texture and increases yield. Once the cream has properly aged, it moves into the heart of butter production, the continuous butter churn. This machine is a long, horizontal cylinder fitted with internal paddles or beaters and designed to replicate the traditional churning motion at industrial scale. As the cream enters the churn, it begins to be violently agitated. The mechanical energy breaks the fat globule membranes, allowing the milk fat to coalesce into larger and larger clusters. Over time, the fat separates from the liquid phase and begins forming visible granules, while the remaining liquid becomes buttermilk. During this stage, the cream undergoes dramatic changes in texture, appearance, and composition. What begins as a smooth, milky liquid becomes a dense, granular mass of butterfat suspended in a yellowish liquid. As this separation proceeds, the machine drains the buttermilk away through a filtered outlet. The buttermilk is collected and sent either for further processing, drying, or use in other dairy products. The butter granules, now much more concentrated, remain in the churn and proceed to a working phase. In a continuous churn system, this working phase takes place in a second chamber, where mechanical kneaders and rollers compress the butter repeatedly, squeezing out remaining moisture and air. This mechanical working aligns the fat crystals, giving butter its smooth and cohesive texture. At this point, salt may be added depending on the product specification. Salt is dosed by weight and mixed evenly using kneading paddles. The inclusion of salt not only impacts flavor, but also improves shelf life by reducing water activity. The butter continues moving through a series of finishing sections. These include vacuum deaerators that remove trapped air bubbles and moisture controllers that adjust water content to match exact legal requirements. For most commercial butters, the moisture content must not exceed 16%, and sensors along the processing line constantly measure this, adjusting kneading speed and vacuum duration to fine-tune the final product. Some systems also pass the butter through a cooling belt or roller press, where its temperature is precisely adjusted for optimum slicing or packaging consistency. Once the butter has reached its final structure and composition, it is directed into the packaging station. Depending on the product line, butter may be formed into rectangular blocks, sticks, tubs, or single-serve portions. For block butter, the butter flows into a volumetric filler that extrudes the product into molds or directly onto a forming belt lined with parchment or wax paper. A synchronized cutter divides the butter into precise portions, which are immediately wrapped in foil or printed paper. These wrappers are folded and sealed mechanically, with batch information and dates inkjet printed on the surface. Tub butter follows a similar path, but the butter is pumped into pre-formed plastic containers using multi-head piston fillers. As each tub is filled, it passes under a lidding machine that applies a foil or plastic seal, followed by a snap-on lid. The sealed tubs are coded, labeled, and pass through vision systems that verify weight, seal integrity, and label position. Any irregular package is immediately removed from the line. The final packaged butter is gathered onto conveyors that lead to case packers. Robotic arms pick and place the butter packs into cartons, which are then sealed, palletized, and wrapped for distribution. Cold chain logistics are maintained throughout the process. Finished butter is stored in cold rooms between 2 degrees C and 6 degrees C to preserve consistency and prevent melting. Forklift trucks or automated guided vehicles move pallets into refrigerated storage or directly onto temperature-controlled transport trucks. Throughout this entire process, quality control is integrated into every stage. Sensors measure fat content, moisture level, temperature, and product density at critical control points. Samples are pulled regularly from the production line and taken to the lab, where technicians evaluate microbial, load, salt dispersion, texture, spreadability, and melting point. Rheology tests may be performed to assess the butter's mechanical behavior under different temperature and pressure conditions. Additionally, sensory analysis is conducted to ensure flavor profile, mouthfeel, and aroma remain within product specifications. Sanitization of the butter line is rigorous and largely automated. Between production runs, clean-in-place systems pump caustic and acid cleaning solutions through the churn, pipes, tanks, and pumps. Rinse water is analyzed to ensure chemical removal, and microbial swabs of the equipment are performed to verify sanitary conditions. Because butter contains high fat content, which can trap and protect bacteria, the entire production environment is kept under strict hygienic controls with positive air pressure rooms, stainless surfaces, and food-grade lubrication on all moving parts. In total, from the moment raw milk enters the facility to the point a stick of butter is packed and cooled for shipping, the process is designed to maintain the integrity of the milk fat while achieving total uniformity. Every kilogram of butter must not only look the same, but spread, taste, and melt in the same way, whether destined for a home kitchen or a commercial bakery. The complexity lies not in a long list of ingredients, but in the tight coordination of time, temperature, agitation, and moisture removal, factors that must be held in careful balance at industrial speeds. Even slight changes in cream fat percentage, aging temperature, churning torque, or packaging temperature can impact the product's shelf life or customer experience. That's why butter factories operate under detailed standard operating procedures, with line operators and quality managers constantly adjusting, calibrating, and reviewing performance data. Computerized control systems archive every data point from each batch, allowing for full traceability and statistical process control. Condensed milk production in a factory follows a linear and tightly regulated process that transforms raw cow's milk into a thick, sweet, shelf-stable dairy concentrate through filtration, heating, evaporation, and canning without ever allowing the product to separate, burn, or ferment along the way. The process begins when whole milk is delivered from dairy collection routes directly into insulated stainless steel storage silos, where the liquid is agitated at low speeds to prevent cream separation while remaining cooled just above freezing to slow bacterial growth before processing. When ready, the milk is pumped into a pre-treatment tank where it undergoes clarification using centrifugal separators, which remove physical impurities like dirt udder cells and stray debris suspended in the milk stream. After clarification, the milk flows through a cream separator, which uses centrifugal force at extremely high speed to separate milk fat from the skim portion with precision controls that allow technicians to blend the separated fat and skim streams back together to reach an exact standardized fat percentage, depending on whether the product is destined to become full cream or partially skimmed condensed milk. Once the desired fat level is achieved, the standardized milk is moved through a plate heat exchanger where it is heated rapidly from storage temperature to a high preheating point around 70 degrees Celsius, which is essential to prepare the milk for pasteurization and evaporation stages, while also helping prevent protein coagulation during boiling. The heated milk is sent through a deaeration chamber, where a controlled vacuum removes dissolved oxygen and volatile gases that could otherwise promote oxidation, darkening, or off flavors during extended heating. Following deaeration, the milk enters the pasteurizer, which is another heat exchanger that brings the product up to at least 85 degrees Celsius for 15 seconds in order to destroy pathogenic bacteria while also denaturing serum proteins, which helps stabilize the milk emulsion during the next phase. The pasteurized milk flows directly into the vacuum evaporator, which is a large multi-effect system of stainless steel vessels, each operating under reduced pressure so that water can boil out of the milk at lower temperatures around 55 to 60 degrees Celsius without scorching the sugars or destabilizing the proteins. The milk moves from one evaporator vessel to the next as the boiling point decreases in each stage, which allows the system to evaporate up to 60% of the water content using much less energy than open boiling. Inside the evaporator, thin film technology spreads the milk into a film across heated surfaces, while vapor separators catch the steam and divert it to a condenser, which turns the vapor back into water and often reuses the heat for incoming milk preheating. At the end of evaporation, the milk exits the chamber as a thick but unsweetened concentrate with a high solid content that resembles heavy cream in appearance, but with a much richer milk protein and sugar density. This partially condensed milk is pumped into a high shear blending tank, where precise amounts of liquid sucrose or refined dry sugar are added and dissolved thoroughly using high-speed impeller mixers that prevent clumping or crystallization. The sugar content is brought to approximately 40 to 45% by weight, which plays a key role in preserving the product by increasing osmotic pressure, which inhibits microbial activity and enables the condensed milk to remain shelf-stable even without refrigeration. At this stage, the sugar also changes the viscosity, mouthfeel, and color of the milk, giving it the signature creamy density and light caramel hue that consumers recognize. After blending, the sweetened condensed milk is passed through a vacuum finisher, which removes any remaining air introduced during mixing and adjusts final moisture content to target specifications. From here, it travels through a homogenizer, where it is forced at high pressure through a narrow valve, which breaks down fat globules and disperses them evenly throughout the mixture, so the final product does not separate during storage. The homogenized condensed milk is then cooled gradually in a plate chiller, which brings the product down from around 60 degrees Celsius to 30 or below, which prevents any further cooking or darkening while preparing it for packaging. The packaging line for condensed milk is built around ultra-clean can filling systems designed to prevent any contamination during the critical transition from liquid product to sealed retail packaging. Empty cans made of tin-coated steel arrive at the filling line pre-cleaned and are inverted and blasted with filtered air before being turned upright again. These cans are conveyed under filling nozzles, which dispense a measured volume of condensed milk into each can based on volumetric or gravimetric control systems, which use load cells or liquid flow meters to ensure every unit is within tolerance. After filling, each can receives a quick blast of saturated steam that pushes residual oxygen out of the headspace before a metal lid is placed on top and sealed using a double seaming machine that rolls and crimps the lid and can body together into a hermetic closure that resists pressure, microbial entry, and spoilage. Sealed cans then pass into a batch or continuous sterilization system where they are heated to specific internal temperatures using steam or hot water sprays inside a pressurized retort chamber. This thermal treatment ensures that any residual microorganisms in the product or on the inner lid surface are destroyed while also stabilizing the proteins and sugars inside the milk. After cooking, the cans are cooled gradually using chilled water or air to avoid thermal shock, which could distort the cans or compromise the seam. As they exit, the sterilizer cans are dried using high-velocity air knives and conveyed to labeling machines, which apply printed labels using hot melt adhesive or shrink sleeves, depending on market requirements. Each labeled can passes through a combination of inspection systems, including metal detectors, to identify any manufacturing debris, vision sensors to confirm label accuracy, and inkjet printers that apply batch numbers and expiration dates directly onto the can body. The finished units are grouped into cartons or trays using robotic arms and shrink-wrapped to form transport-ready units, which are loaded onto pallets by automated palletizers and moved into warehouse storage areas maintained at controlled ambient temperatures to preserve texture and quality before distribution. The factory process is managed by central control systems that log thousands of data points every minute, including product temperature flow rates, moisture levels, and SEMA pressure readings. This data is constantly monitored by quality control teams who take regular samples from each batch and analyze them for fat content, sugar density, total solids, microbial stability, and sensory characteristics like taste color and viscosity. Any batch that falls outside parameters is flagged for review and may be diverted to reprocessing or waste depending on the issue. Mozzarella is made in a factory by taking raw whole cow's milk and transforming it through a series of uninterrupted thermal, mechanical, enzymatic, and physical steps that preserve the integrity of the milk, while turning it into a highly elastic, semi-soft cheese with a clean, stretchable texture and a delicate, milky flavor. And the process begins when fresh milk is delivered to the factory in chilled insulated tankers that offload the milk into stainless steel storage silos, which are tall vertical tanks fitted with internal mixers that prevent the cream from separating, and with chilled plate jackets that maintain a temperature just above freezing to keep the milk in optimal condition before processing begins. The milk is drawn from the silos through automated pipelines and passed through a fine particle filtration system that removes any stray debris or sediment that may have entered during transport, and is then sent through a centrifugal clarifier that spins at high speed to separate any residual solid impurities and to eliminate any air bubbles trapped in the milk, which could interfere with downstream consistency. And once the milk has been clarified, it proceeds to the standardization stage, where it is blended with either skim milk or cream, depending on whether the end product requires full fat or part skim mozzarella. And this is done using inline fat analyzers that control the flow of each stream and continuously adjust the blending ratio to maintain the target fat content within a narrow tolerance. The standardized milk now moves directly to the pasteurization system, which is usually a high-temperature short-time pasteurizer, where the milk is heated rapidly by passing through a series of stainless steel plates with alternating flows of hot water on one side and milk on the other, allowing the milk to reach 72 degrees Celsius and hold that temperature for 15 seconds, which is sufficient to destroy harmful pathogens and deactivate native enzymes that could otherwise affect the flavor and shelf stability of the cheese, and the milk is then cooled immediately to around 35 degrees Celsius, which is the optimal temperature for enzyme and culture addition in the curdling phase. Once cooled, the milk enters a large enclosed cheese vat, which is a rectangular stainless steel tank equipped with slow rotating agitators and submerged temperature probes. And here, a precise amount of starter cultures is added, which begin to acidify the milk and produce lactic acid, gradually lowering the pH, while also contributing to flavor development and structural changes in the protein matrix. And shortly after the cultures are added, a measured dose of liquid rennet is injected into the vat, and the rennet is an enzyme complex that cleaves the casein protein molecules in the milk, causing them to bond together and form a gel-like network that traps fat and water. And this transformation turns the fluid milk into a semi-solid mass called curd within 20 to 40 minutes. The curd is then cut using a series of vertical and horizontal knife blades mounted on rotating frames that sweep through the vat, slicing the gel into uniform cubes, typically 1 to 2 centimeters across. And this cutting action breaks the network apart and begins the release of whey, which is the liquid portion of the milk containing water, lactose minerals, and dissolved proteins. And the curd and whey mixture is stirred slowly while the vat is gently heated either by steam injection or hot water circulation around the jacket walls. And this cooking process firms up the curds, causes them to contract and release more whey, and also prepares the protein structure for the next critical stage, which is stretching. After cooking, the whey is drained from the vat using perforated outlets, and the curds are allowed to settle and consolidate into larger soft clumps, which are scooped or pushed onto a draining conveyor that lifts them out of the vat and allows excess whey to continue draining away, while the curds begin to fuse slightly under their own weight. And the warm curds are then transferred into the pasta filata machine, which is the heart of mozzarella production and is responsible for the cheese's stringy, stretchable texture. The pasta filata system is a series of enclosed chambers and augers where hot water, typically above 80 degrees Celsius, is mixed with the curds, which are then kneaded, pulled, stretched, and folded repeatedly by rotating arms or helical screws. And during this mechanical working process, the heat and movement cause the proteins in the curds to align into long strands while expelling trapped whey and air and forming a smooth elastic mass that can be stretched without breaking. And the timing, temperature, and speed of this step are critical because overworking the curd can make it rubbery, while underworking it will result in a crumbly product. Once the curd mass reaches the ideal stretch consistency, it is directed into forming hoppers, where it is portioned into shapes depending on the product line. And for traditional mozzarella balls, the cheese is extruded through a cylindrical outlet and sliced by a rotating wire into spheres that fall into a chilled water bath, which firms them quickly and prevents sticking. While for block mozzarella, the hot curd is pressed into rectangular molds using pneumatic plungers and cooled in jacketed chillers. And for shredded mozzarella, the cheese is first formed into large logs, then chilled and conveyed to shredding machines fitted with rotary blades that cut the cheese into uniform, thin strips. After forming, the mozzarella must be cooled and sometimes brined, depending on the desired flavor and moisture. And the most common method is to transfer the molded cheese into large water tanks chilled to below 5 degrees Celsius, where the cheese is held for several minutes to stabilize its structure. And in some cases, a salt brine is used instead of plain water, which adds flavor and acts as a mild preservative. And once cooled, the mozzarella is conveyed out of the tank using perforated baskets or belts and allowed to drain briefly before entering the packaging line. For ball mozzarella, the drained cheese is deposited into thermoformed plastic trays or tubs, which may also be filled with brine or protective liquid and sealed under modified atmosphere using a mix of inert gases to reduce spoilage. And for blocks or logs, the cheese is vacuum packed in clear or printed plastic film using heat sealers that extract air and create a tight seal. And for shredded mozzarella, the cheese is dispensed into pre-formed pouches using auger fillers or weigh-scale systems and sealed in nitrogen-flushed bags to maintain freshness. Each packaged unit is labeled with product information batch code and expiry date using thermal printers or laser etching, and passes through metal detectors and X-ray machines that screen for foreign objects. And any rejected packs are diverted automatically for inspection, while approved packs are grouped into cartons by robotic arms loaded onto pallets and stretch wrapped for cold storage. The finished mozzarella is stored in refrigerated warehouses maintained at 2 to 4 degrees Celsius with inventory tracked by barcode scanning, and warehouse management software and distribution is carried out using chilled trucks with temperature monitoring systems that ensure the product arrives at its destination without temperature abuse or textural damage. Throughout the process, the factory is equipped with a supervisory control and data acquisition system that monitors every parameter from milk composition to brine concentration and mechanical torque during stretching, and any deviation from set points, triggers alarms or automatic adjustments to maintain quality and consistency. And samples are pulled at regular intervals for lab analysis, including moisture fat, protein, meltability, stretch tests, and microbial counts. The entire system is built around precision control of temperature movement and transformation, where milk is reshaped molecule by molecule into a cheese that must be soft yet firm, bland yet flavorful, elastic yet sliceable. And the art of mozzarella making lies not in the ingredients, but in the way heat motion timing and alignment are applied with consistency and scale. After packaging the mozzarella, the production process still continues behind the scenes with an extensive chain of post-production systems that ensure each batch remains traceable, consistent, and aligned with food safety standards. And this layer of the factory operation is often invisible to consumers, but plays a vital role in delivering mozzarella that performs identically whether melted on a pizza sliced for retail or shredded into meal kits. And every package that leaves the facility is linked to a batch code which ties it back to the exact milk delivery time, the culture batch, the rennet source, the curd temperature, the stretch torque, and the cooling curve. And these parameters are automatically logged in the plant's data historian system, which stores thousands of data points per hour across every stage of production. Once palletized, the mozzarella products are not randomly stored, but rather sorted according to SKU rotation date, customer order, and temperature requirement using automated storage and retrieval systems that navigate warehouse aisles and place each pallet in an exact location, mapped by a central inventory engine that also manages dispatch scheduling and cold chain routing. And every time a pallet is moved, scanned, or shipped, the information updates in real time, ensuring full visibility of stock movement, shelf life, and logistics coordination. While this logistical control ensures mozzarella flows smoothly from factory to retailer, the factory's maintenance and cleaning cycles are just as important to preserve the high standards required for dairy processing, and every tank pipe belt and conveyor involved in the mozzarella line is subject to clean-in-place cycles, which involve flushing the system with heated alkaline solutions, followed by acid rinses and sterile water. And this process is automated and sequenced with precision to ensure that all internal surfaces are cleaned without the need for manual disassembly, and sensors placed throughout the system confirm the removal of residual proteins, fats, and cleaning chemicals before production can resume. Alongside cleaning factory engineers, conduct regular calibration of weighing systems, temperature probes, stretch tension arms, pasteurizer flow rates, and pH meters to ensure every measurement taken during mozzarella production remains accurate and stable and predictive. Maintenance is also applied where sensors monitor vibration temperature and cycle count on critical components such as churn drives, pump shafts, and forming blades to identify wear before it becomes a problem, allowing for downtime planning and parts replacement with minimal impact to production. The history of nerds stretches back to the early 1980s, when they were first introduced to the market as a playful, intensely flavored treat unlike anything else in the candy aisle. The appeal lay in their irregular shapes, their bright colors, and their signature combination of sweet and sour notes. Behind the scenes, however, the magic is created not by whimsy, but by a carefully controlled industrial process. It all begins with the sourcing of raw ingredients. The foundation of nerds is refined cane or beet sugar, which arrives at the factory in bulk deliveries, often in multi-ton silos or in large paper sacks that are emptied into storage hoppers. This sugar is highly refined to ensure purity, with a moisture content so low that it will not clump during storage or handling. Alongside the sugar come shipments of corn syrup, which acts as a binding and texturing agent, as well as citric acid and malic acid to provide the tartness that defines Nerd's flavor profile. The plant also receives concentrated flavor oils and powdered colors approved for food use. Each batch of these ingredients is tested in a quality control laboratory before it enters the production stream, ensuring compliance with both flavor and safety standards. The production of Nerds begins with a core, which is essentially a tiny granule of sugar that serves as the seed for the candy's build-up process. These seed crystals are often derived from slightly coarser sugar grains that have been screened to a uniform size. The real artistry begins in the heart of the coating pans, large rotating drums that are the beating heart of sugar candy manufacturing. Inside these stainless steel pans, the sugar seed crystals are gently tumbled as a fine mist of sugar syrup is sprayed over them. This syrup is prepared in a heated mixing tank, where granulated sugar is dissolved into water under controlled temperature, often in the range of 110 to 130 degrees Celsius, and then blended with a precise amount of corn syrup to control crystallization. The hot syrup flows through jacketed piping to prevent premature cooling before being atomized into a fine spray within the coating pan. As the syrup coats the tumbling seed crystals, it begins to harden upon contact with the cooler air inside the pan, forming a thin outer layer. Then, a light dusting of dry sugar is sometimes added to further build the surface and maintain separation between individual granules. This cycle repeats dozens or even hundreds of times, each layer adding microns of thickness to the growing candy piece. Operators closely monitor airflow, humidity, and drum rotation speed to ensure that the candies do not stick together or form unwanted lumps. During this stage, the irregular shapes that make Nerds so distinctive begin to emerge. Unlike machine-molded candies that have identical geometry, these sugar-coating pans produce slight variations in size and contour, which means every Nerd has its own unique outline. The gradual layering process continues until the candy reaches the target size, which is typically just a few millimeters in diameter. Once the base size is achieved, flavoring and coloring are introduced. This is a delicate operation, as liquid flavors and colorants must be distributed evenly without dissolving the sugar surface. The pan operator reduces airflow slightly and sprays a concentrated solution of flavor oils, acids, and color onto the candy bed. In many cases, flavors are applied in small incremental sprays with pauses for tumbling in between, allowing the surface to dry and preventing color streaking. The flavors are carefully balanced so that the acids provide tang without overwhelming the sweetness, creating the signature taste that fans recognize instantly. After flavoring and coloring, the candies undergo a polishing step. This involves applying a thin layer of glazing agent, such as carnauba wax, which gives the Nerds their characteristic sheen and helps protect them from moisture pickup during storage. The glaze is applied in a separate polishing pan, where candies are tumbled with a small amount of the molten wax until every piece has a uniform shine. At this point, the candies are allowed to cool and set fully, ensuring that their coatings have hardened completely. Cooling may occur in ambient air or in a temperature-controlled chamber that maintains low humidity to prevent stickiness. The fully cooled candies are then transferred via gentle vibratory conveyors to the packaging area. The packaging operation for Nerds is an impressive example of precision weighing and high-speed filling. Because the candy pieces are so small and irregular, multi-head weighers are commonly used to ensure accurate portioning. These machines use multiple load cells arranged in a circular pattern, dropping small amounts of candy from each channel until the combined total matches the target weight. This system minimizes giveaway and ensures that each box contains exactly the promised amount. The iconic Nerds boxes are constructed from food-grade cardboard with an inner lining that protects against moisture. The packaging line begins by folding and gluing the flat printed cartons into their box shape, often with automated carton erectors that can handle hundreds of units per minute. The weighers then deposit the precise quantity of candy into each box through stainless steel chutes. For dual flavor boxes, a partition is inserted inside the carton, and two separate weighing heads feed different candies into each side simultaneously. Once filled, the boxes pass through a closing station, where flaps are folded and glued shut, followed by a coding station that prints lot numbers and best before dates for traceability. The sealed boxes are then collated into larger trays or shrink-wrapped bundles for ease of handling in distribution. Quality control continues all the way through the process. In addition to the raw ingredient checks at the start, samples of candy are pulled from the line at regular intervals to assess flavor consistency, color uniformity, and physical integrity. The hardness of the coating is measured with specialized instruments, and the acidity levels are checked to ensure the sourness remains within the brand's signature profile. Metal detectors are integrated into the conveyor system to ensure no foreign materials make their way into the final product. From the packaging area, the candies move to the warehouse for distribution. Since Nerds are low in moisture and have a hard sugar shell, they are relatively stable during storage. However, they are kept in a cool, dry environment to maintain their texture and prevent color fading. Pallets of finished product are wrapped and staged for shipment to wholesalers, retailers, and export markets around the world. The journey from sugar seed to the vibrant, tangy pellets in your hand is a testament to how much engineering is hidden inside even the simplest candies. Each step, from syrup spraying in massive tumbling pans to the delicate flavor infusion and high-speed filling lines, is executed with precision to deliver the playful, crunchy experience that has kept Nerds popular for decades. Over time, manufacturing technology for Nerds has evolved to improve efficiency and consistency. Early production relied heavily on skilled operators adjusting pans by sight and sound. Today, advanced automation systems track humidity, airflow, and syrup application rates with sensors and feedback loops, ensuring that every batch meets exacting standards. The result is a product that remains faithful to its original flavor and texture while benefiting from modern advancements in food processing equipment. There is also increasing focus on sustainability in candy production. Many factories now recover and reuse heat from syrup cooking kettles, implement water-saving cleaning systems for coating pans, and work with suppliers to source sugar from more sustainable agricultural operations. Packaging too is being reevaluated, with lighter materials and improved recyclability being considered for the future. What makes the production of Nerds especially fascinating is the balance between art and science. The process is rooted in classical confectionery techniques that date back centuries, yet it is executed on a scale and with a precision that only modern machinery can achieve. The slight variations in size and shape that give Nerds their charm are not flaws, but deliberate results of the panning process, embraced as part of their identity. The story of Twizzlers begins long before the candy reaches the factory floor. As with many mass-produced confections, The foundation is in the sourcing of high-quality raw materials. The primary ingredient is refined wheat flour, which gives Twizzlers their chewy, slightly bread-like texture. This flour arrives at the plant in bulk tanker trucks and is stored in towering silos that protect it from moisture and contaminants. From here, it is gravity-fed or pneumatically conveyed through sealed pipes to the mixing area. Alongside flour, the recipe calls for corn syrup, which provides sweetness, binding power, and flexibility, as well as sugar, which boosts flavor and adds structure. Vegetable oil, often in the form of soybean or palm oil, contributes to the mouthfeel, while food-grade colors and flavorings give Twizzlers their signature appearance and taste. Every ingredient undergoes rigorous inspection in the quality control laboratory before it can be released to production. Flour samples are checked for protein content and moisture levels. Sugar is screened for crystal uniformity, and corn syrup is tested for viscosity and purity. Liquid flavors and colors are reviewed for consistency against reference standards. Once approved, ingredients move into the blending stage, where the transformation from raw material to candy dough begins. The mixing process takes place in large stainless steel horizontal mixers fitted with heavy-duty paddles or spiral blades. The operation starts with a precise ratio of flour and sugar being combined, followed by the gradual addition of corn syrup and water. These mixers operate under controlled speeds to ensure the dough develops evenly without excessive heat buildup. Oil is incorporated next, coating the flour particles and contributing to the dough's smooth, pliable consistency. Throughout mixing, operators monitor temperature and dough texture, making small adjustments to moisture content if necessary. In many plants, this step is partially automated, with sensors tracking torque resistance in the mixer to determine when the dough has reached the ideal elasticity. Once mixed, the candy dough is transferred to the extrusion line. This is the stage where Twizzlers take on their famous twisted rope form. The dough is fed into a large extruder, essentially a high-powered screw press that forces the material through a specially designed die. The screw inside the extruder rotates at a controlled speed, kneading and pushing the dough forward while maintaining an even temperature to prevent premature setting. At the end of the barrel, the die features multiple openings shaped to produce the exact cross-section of a Twizzler rope. For the classic variety, the die includes ridged channels that create the candy's spiral grooves. As the dough emerges from the die, it is still warm and soft, making it easy to shape but vulnerable to deformation. To preserve the precise geometry, the extruded ropes immediately enter a cooling conveyor, a long belt that passes through a tunnel where chilled, dehumidified air circulates. This step lowers the candy's temperature and sets the outer surface while maintaining a chewy interior. The speed of the conveyor is carefully calibrated so that cooling is uniform along the rope's entire length. An interesting detail of Twizzlers' production is that the twist in each rope is not solely a result of the die design. The conveyor belt itself may be equipped with rollers that gently rotate the ropes as they move forward, enhancing the spiral effect. The amount of twist is a delicate balance. Too much rotation can weaken the structure and cause breakage, while too little results in a less distinctive look. After cooling, the ropes are ready to be cut to size. Cutting is performed by high-speed guillotine blades or rotary knives synchronized with the conveyor movement to avoid crushing the candy. For standard snack-sized Twizzlers, lengths are typically between 6 and 8 inches, but the same line can be adjusted to produce miniature bites or extra long versions. The cut pieces now move towards the packaging area, but before they are boxed or bagged, they undergo inspection. Quality control technicians pull samples from the line to check twist uniformity, diameter, weight, and surface texture. The moisture content is measured to ensure the candy retains its chewiness during storage. Flavor is also evaluated by trained sensory panels who compare each batch to established taste profiles. Packaging Twizzlers is a study in efficiency. Depending on the product format, they may be wrapped in flexible plastic film, placed in cardboard trays, or sealed in resealable pouches. The packaging machinery begins with an in-feed system that gently aligns the ropes into uniform stacks. These stacks are then transferred into forming tubes where the plastic film is drawn around them, sealed along the edge with heat, and cut into individual packs. Heat-sealed jaws close the ends to lock in freshness and protect the candy from moisture and oxygen. Lot codes, manufacturing dates, and product identifiers are printed directly onto the packaging by inkjet or thermal printers, ensuring traceability for every unit. Sealed packages are collected onto a takeaway conveyor and then collated into larger cartons for shipping. These cartons are stacked on pallets by robotic palletizers, which arrange the boxes in stable patterns and wrap them in stretch film to secure the load. From here, the pallets are moved to the warehouse, a temperature-controlled environment designed to maintain product quality. Although Twizzlers are relatively stable due to their low moisture and high sugar content, excessive heat can cause surface stickiness or deformation, so storage temperatures are carefully regulated. The finished products are then shipped to distribution centers, retail outlets, and export markets. Behind all of this is a network of automation systems and process controls that keep production running smoothly. Modern Twizzlers plants rely on programmable logic controllers to coordinate mixer cycles, extrusion pressures, conveyor speeds, and packaging rates. These systems integrate with quality control data, enabling operators to adjust parameters in real time if a batch shows signs of deviation from the standard. The flavoring of Twizzlers deserves special mention. While the classic strawberry variety is the most famous, the process allows for a wide range of flavors, from cherry to chocolate to licorice. In each case, the flavor oils are blended into the dough at the mixing stage to ensure even distribution. The choice of flavor affects other parameters as well. For example, chocolate varieties may require a slightly different extrusion temperature due to the fat content in cocoa powder, while licorice varieties may use molasses or anise oil that alter dough handling characteristics. Over the years, Twizzlers production has been refined not only for efficiency, but also for consistency. Early methods required more manual handling, with operators guiding ropes off the extruder and cutting them by hand. Today's operations are highly automated, with minimal direct contact between workers and the product. This not only improves hygiene, but also allows for higher output with fewer defects. Sustainability is becoming a greater focus in candy manufacturing as well. Plants are investing in closed-loop water systems for cooling conveyors, energy-efficient ovens for any heat treatment steps, and waste reduction programs that recycle off-spec candy back into the mix when feasible. Packaging materials are also being evaluated for recyclability, with thinner films and plant-based plastics under consideration. What makes the Twizzlers process so fascinating is the combination of bakery-like dough handling with candy-making sweetness. The extrusion technology is similar to that used in pasta production, yet the ingredients and post-extrusion handling are firmly rooted in confectionery science. It is a hybrid process that demands both mechanical precision and an understanding of how sugars, starches, and fats interact under heat and pressure. When you pick up a pack of Twizzlers, you are holding the result of careful ingredient selection, finely tuned mixing and extrusion, precise cooling and twisting, and airtight packaging. Each rope is the product of countless micro adjustments in speed, temperature, and formulation that ensure the candy's texture, flavor, and appearance are exactly as consumers expect. The story of a Haribo gummy begins with the ingredients, each of which is selected for quality and consistency. At the heart of the recipe is gelatin, a protein derived from collagen that gives the candy its characteristic elastic texture. This gelatin arrives at the factory in dry, granulated form and must be carefully hydrated before use. Alongside gelatin, the formulation includes glucose syrup, often produced from wheat or cornstarch, which provides body, prevents crystallization, and contributes to the chewiness. Sugar is another mainstay, giving sweetness and structural integrity. Additional ingredients include citric acid for tartness, natural and artificial flavorings for each variety, and food-safe colorants to create the rainbow of hues that define Haribo's product line. Every batch of ingredients undergoes rigorous testing in a quality control laboratory before it reaches the main production floor. Gelatin is checked for bloom strength, which determines the firmness of the finished candy. Glucose syrup is tested for solids content and viscosity, ensuring it will flow and set properly in the cooking process. Flavor and color concentrates are measured for potency and compared against established standards. Only when the raw materials pass inspection are they released to the production team. The first major step in making Haribo gummies is the cooking process. This begins in large stainless steel vessels called dissolvers or cooking kettles. Here, sugar, glucose syrup, and water are combined and heated under controlled conditions. The heating process brings the mixture to a high temperature, often in the range of 110 to 140 degrees Celsius, allowing the sugars to dissolve completely and the syrup to thicken. Once the sugar syrup reaches the correct density, pre-soaked gelatin is added. The gelatin is never boiled, as high temperatures would damage its gelling properties. Instead, it is stirred in gently once the syrup has cooled to a safe range, typically between 80 and 90 degrees Celsius. At this point, flavorings, acids, and colors are added. For gummy bears, this might include lemon, orange, raspberry, apple, and strawberry flavor profiles, each paired with a corresponding color. The additives are metered in with precision pumps to ensure every batch is consistent in both taste and appearance. Stirring must be thorough but gentle to avoid incorporating excess air bubbles, which could mar the candy's surface. Once the mixture is fully blended, it is ready to be formed into shapes. This is where Haribo's distinctive starch molding process comes into play. The company uses a method called the Mogul system, an automated production line that allows liquid candy to be deposited into detailed molds with incredible precision. The process begins with large trays filled with a fine, dry cornstarch powder. This starch serves two purposes. It prevents the sticky candy from clinging to the trays, and it helps wick away excess moisture during the setting stage. Each tray passes through a stamping unit where metal dies press the shape of the candy into the starch. Tiny, bare outlines, cola bottle profiles, or whatever form is being produced. The impressions are crisp and exact, ready to receive the warm, liquid mixture. From the cooking kettles, the candy syrup is pumped through heated pipelines to a series of depositor nozzles. These nozzles align perfectly with the starch impressions and release measured amounts of syrup into each cavity. The depositor can switch flavors and colors quickly, allowing for multiple varieties to be produced on the same line with minimal downtime. Once deposited, the trays of liquid candy are conveyed into a long climate-controlled curing room. Here, they rest for 12 to 72 hours, depending on the recipe, temperature, and humidity. During this time, the gelatin network fully sets, giving the candy its final chewy texture, while the starch continues to absorb surface moisture. The curing rooms are kept at specific humidity levels to prevent the candies from drying out too much or becoming sticky. When curing is complete, the trays move to the demolding stage. The gummy shapes are gently lifted from the starch, which is recovered, dried, and sieved for reuse in future molding. Any excess starch clinging to the candies is removed through a combination of mechanical shaking and soft air jets. The gummies, now fully formed, have a matte appearance and a slightly tacky feel at this stage. To give them the glossy finish consumers recognize, the candies are transferred to large rotating drums called glazing pans. Inside, they are tumbled with a thin coating of food-grade waxes such as carnauba or beeswax, along with oils that enhance shine and prevent sticking. The glazing process is quick but crucial, as it also provides a protective barrier against moisture changes during storage. With their appearance perfected, the gummies proceed to the packaging area. Here, high-speed conveyors feed them into multi-head weighers, machines equipped with multiple hoppers that dispense exact amounts to achieve the target package weight. The candies are dropped into pre-formed bags or into the forming tubes of vertical form-fill-seal machines. These machines create a bag from a continuous roll of printed film. Seal the bottom, fill it with the candy, then seal the top in one continuous motion. For variety packs, sophisticated sorting systems group different gummy shapes and flavors in precise ratios before they reach the weighing step. This ensures that every bag contains the intended assortment. Packaging films are chosen for their barrier properties, keeping the gummies fresh while displaying bright branding. Each bag receives a lot code and best before date for traceability, then passes through metal detection equipment as a final safety measure. The finished bags are gathered into cartons, stacked onto pallets, and wrapped in stretch film to stabilize them for shipping. Pallets are moved to temperature-controlled storage areas until they are loaded onto trucks bound for distribution centers and retailers around the world. Throughout the entire process, quality control remains a constant presence. Samples from each batch are taken at multiple points, from syrup cooking to molding, curing, and packaging, to ensure that every aspect meets Haribo's specifications. Technicians test texture with penetrometers to confirm the perfect chew, measure pH to monitor acidity, and use colorimeters to verify hue accuracy. Flavor panels taste test samples to ensure the product matches established sensory profiles. The production of Haribo gummies has evolved significantly over the decades. Early batches were made by hand in small copper kettles and poured into starch molds one tray at a time. Today's lines can produce hundreds of thousands of pieces per hour, with computerized systems controlling every variable. Yet the core principles remain the same: quality ingredients, precise cooking, careful molding, and patient curing. There is also a growing emphasis on sustainability within Haribo's operations. Many plants now use energy recovery systems to capture heat from cooking processes, recycle starch indefinitely, and source gelatin and sugar from more sustainable supply chains. Efforts to reduce packaging weight and increase recyclability are also underway, ensuring that the joy of gummy bears has a smaller environmental footprint. What makes Haribo's process fascinating is the blend of old-world confectionery craftsmanship and high-tech automation. The mogul molding system, for instance, is an industry standard, yet it still relies on principles that candy makers have used for over a century. The long curing time is a reminder that some aspects of candy making simply cannot be rushed if the desired texture is to be achieved. By the time a bag of Haribo gummies reaches the shelf, it has undergone a transformation from raw sugar, syrup, and gelatin into a perfectly shaped, flavorful, and brightly colored treat. Behind each piece is a network of ingredient sourcing, controlled cooking, precision molding, and patient curing, all supported by layers of quality control and packaging expertise. Nutella's key ingredients are hazelnuts, sugar, palm oil, cocoa solids, skimmed milk powder, whey powder, lecithin as an emulsifier, and vanillin as a flavoring agent. Each of these ingredients is sourced globally, selected for consistency, taste, and availability. Hazelnuts, the signature ingredient, are predominantly sourced from Turkey, which produces more than 2/3 of the world's supply. However, Italy, Chile, and the United States also contribute to the global hazelnut harvest. Ferrero, the company behind Nutella, maintains long-term relationships with growers, and has implemented traceability programs to ensure that hazelnuts meet quality standards for moisture content, size, and taste. Upon arrival at the processing facility, hazelnuts go through rigorous inspection and sorting procedures. This is a critical control point because the quality of the nut directly affects the flavor and texture of the final product. Optical sorters and vibrating sieves are used to remove debris, stones, and underdeveloped nuts. The selected hazelnuts are then subjected to a deshelling operation using mechanical crushers that crack the shells without damaging the kernels. These kernels are further inspected and cleaned before being sent to large-scale roasting units. Roasting is one of the most important flavor development stages in Nutella production. In industrial operations, continuous roasting ovens are used, where hazelnuts travel through a rotating drum or along a conveyor belt under a flow of hot air, typically between 140 to 160 degrees Celsius. Roasting duration and temperature are carefully controlled to bring out the nutty aroma and to reduce moisture to below 5%. After roasting, the nuts are cooled quickly to preserve their volatile aromatic compounds and prevent overcooking. The cooled hazelnuts are then transferred to grinding machines, where they are ground into a paste using roller mills and high-speed grinders. The result is a fine hazelnut paste with a smooth texture ready to be incorporated into the final mix. Meanwhile, other key ingredients are prepared in parallel. Sugar, which makes up a significant portion of the spread, is delivered in bulk as granulated white sugar. Before use, the sugar is pulverized in industrial fine grinders or pin mills until it becomes a powdered form with consistent particle size, often below 30 microns, to avoid any grittiness in the final texture. This powdered sugar is stored in silos and fed into the mixing tanks using pneumatic conveying systems. Cocoa solids, another essential ingredient, are typically received as cocoa powder. This powder undergoes sifting and magnetic separation to remove any foreign particles or metallic fragments. Skimmed milk powder and whey powder, both derived from dairy processing, are reconstituted into a slurry with water or added in dry form depending on the plant design. These milk-based ingredients contribute not only to flavor, but also to the creamy mouthfeel and protein content of the spread. Palm oil is selected for its semi-solid consistency at room temperature, which is ideal for producing a spreadable product that does not require refrigeration. Before blending, palm oil is filtered and heated to a controlled temperature to ensure uniform mixing. It is pumped into heated storage tanks, where it is kept in liquid form and circulated to prevent crystallization. Once all base ingredients are prepared, the process of mixing begins in large-scale stainless steel mixing tanks. These tanks are fitted with high-torque agitators and precision load cells that measure the exact quantity of each ingredient added. The powdered sugar, hazelnut paste, cocoa powder, milk powder, and palm oil are introduced sequentially, followed by small quantities of lecithin and vanillin. Lecithin acts as an emulsifier, allowing the fat-based palm oil to bind with the water-based milk components, ensuring the product remains stable and homogeneous. Vanillin, a synthetic or natural flavoring, gives Nutella its distinct sweet aroma. The mixture is subjected to a refining process to achieve the desired texture and particle size. This is often accomplished using 5-roll refiners or conching machines. The 5-roll refiner uses a series of precision-engineered steel rollers that progressively grind the mixture to a fine, uniform consistency, typically achieving particle sizes of around 20 microns. This stage is crucial for eliminating any detectable graininess, resulting in the smooth, velvety texture Nutella is known for. In some facilities, a conching step follows refining. In conching, the mixture is kneaded and aerated for several hours in large heated vessels. The process further develops flavor, reduces acidity, and allows volatile off flavors to evaporate. Temperature, shear force, and mixing speed are all tightly controlled to maintain product consistency. After conching, the mixture is cooled slowly to prevent separation and to stabilize the emulsion. Once the spread reaches the correct viscosity and temperature, it is pumped through sanitary pipelines to the filling stations. Filling lines are fully automated and consist of synchronized conveyor systems, rotary fillers, and capping machines. The jars, made from glass or plastic, are cleaned with compressed air or ionized air blowers before being filled. Filling heads dispense the exact amount of Nutella into each jar with remarkable precision, ensuring minimal variation between units. Immediately after filling, jars pass through a sealing station where a foil membrane is applied to the mouth of the jar. This step is critical for maintaining freshness and preventing microbial contamination. The foil seal is typically induction sealed using a non-contact electromagnetic process that heats the foil and causes it to bond to the jar rim. Once sealed, the jars are capped with tamper-evident lids and conveyed to labeling machines. High-speed labelers apply brand-specific labels with information such as batch number, expiration date, and ingredients. Each jar then proceeds through a series of quality control checkpoints. These include weight checks, vision systems to verify correct sealing and labeling, and metal detection to ensure product safety. Defective units are automatically rejected and diverted for reprocessing or disposal. The entire packaging area is designed with hygiene in mind, using positive air pressure zones, clean-in-place systems, and stainless steel surfaces to reduce contamination risk. After packaging, Nutella jars are grouped into cartons or shrink-wrapped multi-packs, then stacked on pallets using robotic arms. Pallets are stretch-wrapped and labeled with barcodes for inventory tracking. From here, the product enters the distribution phase. Nutella's distribution logistics are a finely tuned operation. Pallets are stored temporarily in climate-controlled warehouses where temperature and humidity are maintained to prevent oil separation or spoilage. Inventory management systems track product movement using real-time data. Distribution centers coordinate with retailers, wholesalers, and export logistics to move products efficiently. Nutella is shipped in refrigerated or insulated containers only when necessary, though its high fat, low moisture content gives it considerable shelf stability. Throughout its supply chain, Nutella maintains compliance with international food safety standards such as ISO 22000, BRC, and HACCP protocols. Auditors regularly inspect facilities for compliance, and the entire process from hazelnut sourcing to jar sealing is documented for traceability and recall readiness. Automation, data collection, and machine learning are increasingly used to optimize processes, predict maintenance needs, and reduce waste. What makes Nutella's production so compelling is the precise synchronization of global sourcing, advanced food engineering, and automation technologies that allow for the consistent output of millions of jars per day. Every batch is a result of not just culinary science, but also the collaboration of agronomists, engineers, food technologists, and supply chain experts. Beyond the factory floor, Nutella's evolution continues with reformulations aimed at reducing sugar or incorporating more sustainable palm oil. Efforts to use recyclable packaging and implement blockchain for ingredient tracking reflect broader industry trends towards transparency and environmental responsibility. The foundation of Jif begins with its primary ingredient, peanuts. Specifically, the variety used in commercial peanut butter production is often the runner peanut, prized for its uniform kernel size, mild flavor, and high oil content. These peanuts are primarily grown in the southeastern United States, including states like Georgia, Alabama, and Florida, where sandy soils and warm climates create optimal growing conditions. Jif, owned by the J.M. Smucker Company, works closely with peanut growers through long-standing contracts to ensure consistent quality and supply. Before the peanuts even reach the factory, they're subjected to extensive grading systems operated by the USDA, evaluating factors like kernel size, moisture content, and damage from mold or pests. Once harvested, the raw peanuts are cured by drying them to a safe moisture level, usually around 10%. This drying stage is essential to prevent mold growth during transport. The peanuts are then shelled using mechanical shellers that crack the outer holes while leaving the kernels intact. After shelling, the peanuts are cleaned using air classifiers and vibrating screens to remove debris, dirt, and remaining shell fragments. These cleaned kernels are then transported in bulk to Jif's dedicated peanut butter production facilities, where their transformation truly begins. Upon arrival at the factory, peanuts undergo a second round of cleaning and quality control. Optical sorters equipped with high-speed cameras and sensors scan each peanut at astonishing rates, removing any discolored, damaged, or foreign material contaminated nuts. Metal detectors are also employed at this stage to ensure there are no traces of metal debris from harvesting equipment. These steps are critical not only for food safety, but also for maintaining Jif's smooth and consistent flavor. The next stage is roasting, arguably the most important phase for flavor development. Industrial peanut roasters are highly sophisticated machines capable of handling thousands of pounds of peanuts per hour. Jif uses a continuous dry roasting process where peanuts are evenly fed onto a perforated conveyor belt that moves through a tunnel of hot, forced air. Temperatures during roasting typically range between 160 and 180 degrees Celsius, with exact values finely tuned based on peanut size, oil content, and desired flavor profile. This process typically takes 15 to 30 minutes and is closely monitored using infrared sensors and real-time moisture analyzers. As peanuts roast, their proteins and sugars undergo Maillard browning, creating hundreds of volatile aroma compounds that contribute to peanut butter's distinctive roasted flavor. Immediately after roasting, the peanuts are rapidly cooled using chilled air blowers to stop the cooking process and lock in the developed flavors. This cooling also prevents oil separation and oxidation, both of which can negatively impact product shelf life. At this point, the roasted peanuts are ready to be ground, but first they must be blanched. Blanching in peanut butter production refers not to cooking in water, but to the mechanical removal of the thin, papery red skins that surround the kernels. In Jif's facilities, peanuts are sent through dry blanchers, machines that tumble the nuts at high speeds while heated air loosens the skins. Rotating brushes then remove the skins entirely, and high-capacity vacuum systems suck away the debris. The blanched peanuts are now a light golden color and are inspected one final time before grinding. The grinding stage is where peanuts are turned into a thick, luscious paste. Jif's production lines use a two-stage grinding process to achieve the brand's famously smooth consistency. First, peanuts are coarse ground using heavy-duty industrial grinders. These machines use stainless steel burrs or hammer mills to crush the nuts into a semi-solid mass known as peanut paste. This paste still contains some coarse particles and has not yet achieved its final texture. Next, the coarse paste is fed into ultra-high-speed fine grinders, often colloid mills, which apply extreme shear forces to reduce particle size down to 10 to 15 microns. This is a crucial target, as particle size below 20 microns ensures a mouthfeel that is perceived as completely smooth by consumers. During this stage, other ingredients are also introduced into the mixture. These include sugar, fully hydrogenated vegetable oils, salt, and sometimes molasses or mono and diglycerides. The oils, often made from rapeseed, cottonseed, or soybean, are used to stabilize the peanut butter and prevent oil separation on the shelf. Unlike palm oil or liquid vegetable oil, fully hydrogenated oils remain solid at room temperature and help give Jif its stable texture without requiring stirring. These additional ingredients are metered in with extraordinary precision using automated dosing systems connected to load cells and flow meters. Inline mixers ensure that each component is fully dispersed throughout the peanut paste. The temperature during grinding is carefully controlled, typically held between 60 and 75 degrees Celsius, to keep the product fluid without degrading flavor compounds. Once the peanut butter has been ground to the desired texture and all ingredients are thoroughly incorporated, it enters a holding tank under nitrogen blanketing. This protective gas layer prevents oxidation and helps preserve freshness during the short holding period before packaging. The product is then pumped to the filling lines through a network of heated sanitary stainless steel piping. Jif's packaging lines are models of efficiency and automation. Plastic jars, blow molded from PET or HDPE, are automatically unscrambled and conveyed into position. Before filling, jars pass through an air rinse station that uses ionized air to remove dust or plastic fragments. High-speed rotary piston fillers dispense precise volumes of peanut butter into each jar, minimizing air entrapment to avoid spoilage and maintain shelf life. Filled jars are then capped immediately using torque-controlled capping heads that screw on tamper-evident lids. After capping, jars pass through induction sealers where a foil membrane is bonded to the jar rim. This step uses electromagnetic energy to heat and seal the foil in milliseconds, creating a hermetic barrier that locks in flavor and protects against microbial contamination. The sealed jars move to labeling machines, where front and back labels are applied, followed by laser or inkjet printers that mark each jar with batch codes, production dates, and plant IDs. Throughout this packaging process, quality control is constant and rigorous. Automated vision systems inspect each jar for correct fill height, proper labeling, and cap placement. Metal detectors and X-ray scanners identify any contamination before product leaves the factory. Random samples are also pulled for texture analysis, oil separation testing, sensory panels, and microbiological screening. Any deviation from specifications leads to immediate corrective actions, and defective jars are removed from the line. Packaged jars are grouped into corrugated cardboard cases using robotic case packers. These cases are palletized by programmable robotic arms and stretch wrapped to ensure stability during transport. Each pallet receives a barcode label integrated into Jif's warehouse management system, allowing for real-time traceability from production to point of sale. Once palletized, the finished peanut butter is moved to distribution centers equipped with temperature and humidity control. Although Jif peanut butter is shelf-stable and does not require refrigeration, maintaining moderate temperatures during warehousing and shipping helps preserve flavor and prevent oil migration or texture degradation. From these central hubs, Jif is shipped to retailers, wholesalers, and export customers across the country and around the globe. The journey from raw peanut to finished jar is guided not only by mechanical precision, but also by a deep understanding of food chemistry, microbiology, logistics, and consumer expectations. Behind the familiar red-lidded jar is a network of engineers, food scientists, supply chain analysts, and production operators, all working in synchrony to ensure that every spoonful of Jif meets exacting standards. Advancements in automation and data analytics continue to refine the process. Modern Jif facilities are equipped with real-time monitoring systems, predictive maintenance software, and even machine learning algorithms that optimize roasting profiles based on moisture content and kernel density. Environmental controls ensure energy efficiency and waste reduction, and partnerships with peanut growers include sustainability initiatives aimed at soil conservation and water use reduction. The story of Hershey's syrup begins with its core ingredients: cocoa, sugar, water, corn syrup, salt, preservatives, and a few functional additives like potassium sorbate and xanthan gum. Each of these components is sourced with meticulous care to ensure consistency and food safety. Cocoa powder, the primary flavoring agent, is typically sourced from West Africa, where the Hershey company partners with certified cooperatives to encourage sustainable farming practices. The cocoa beans are fermented, dried, and shipped to the US, where they are roasted, ground, and pressed into cocoa cake. This cake is then pulverized into a fine cocoa powder, standardized for fat content, flavor profile, and color intensity. Upon arrival at Hershey's syrup production facilities, all ingredients undergo rigorous testing. The cocoa powder is checked for microbiological safety, color consistency, particle size, and moisture levels. Sugar, often in granulated form, is tested for crystal uniformity, purity, and absence of foreign materials. Corn syrup, used as both a sweetener and thickener, is delivered in tanker trucks and stored in heated silos. It is continuously circulated to prevent crystallization or microbial growth. Water used in the process is treated on-site, filtered, softened, and sanitized using UV light or reverse osmosis to ensure purity and microbial control. The first major production stage is blending the dry and liquid ingredients. The process typically starts with the creation of a sugar corn syrup slurry. In large stainless steel jacketed mixing tanks, granulated sugar is combined with warm water and corn syrup under controlled agitation. These tanks are equipped with variable speed mixers and internal temperature sensors to maintain optimal dissolution rates. The heating jackets help bring the mixture to a consistent temperature, usually between 55 and 70 degrees Celsius, to accelerate solubility while avoiding caramelization. Once a uniform syrup base is achieved, cocoa powder is added. However, dry cocoa is notoriously difficult to hydrate due to its high fat content and fine particle size, which cause it to float and form lumps when introduced to liquid. To overcome this, Hershey's production lines utilize high shear mixers and vacuum-powered powder feeders. The vacuum system pulls cocoa powder directly into the liquid stream, minimizing clumping and ensuring uniform dispersion. Simultaneously, high-speed rotor-stator mixers or inline homogenizers shear the mixture at thousands of RPMs, breaking down any agglomerates and producing a velvety, uniform chocolate syrup base. At this stage, salt and preservatives such as potassium sorbate are also introduced. These additions are precisely dosed using automated ingredient hoppers that weigh each component before releasing it into the blanders. Potassium sorbate acts as a mold and yeast inhibitor, extending the product's shelf life. Some formulations may also include citric acid or sodium citrate to adjust pH, which affects both microbial stability and flavor brightness. The syrup then enters the cooking phase. Unlike batch cooking in traditional kitchens, industrial syrup production uses continuous flow heating systems. The chocolate slurry is pumped through tubular or plate heat exchangers, where it is heated rapidly to pasteurization temperatures, typically between 85 and 95 degrees Celsius. This thermal treatment destroys any remaining microbial contaminants and activates the emulsifiers and stabilizers added in earlier steps. The product is held at this temperature for a specific dwell time as it flows through holding tubes, ensuring regulatory compliance with pasteurization standards. After cooking, the syrup must be cooled quickly to prevent overcooking and maintain the desired viscosity and flavor. This is achieved using chilled water heat exchangers, which rapidly bring the syrup down to below 30 degrees Celsius. Rapid cooling also helps stabilize the emulsion, locking in the texture and preventing ingredient separation. The cooled syrup is then transferred to intermediate holding tanks, where it is gently agitated and blanketed with nitrogen gas to minimize oxidation. At this point, the syrup undergoes several quality control checks. Samples are pulled and tested for viscosity using rotational viscometers, ensuring that the pourability matches the brand's standard profile. Colorimeters assess chocolate intensity and hue, while refractometers measure sugar concentration. In parallel, sensory panels may be employed to evaluate flavor, mouthfeel, and aroma. Microbial testing is conducted on every batch to confirm that pasteurization was effective and that no contamination has occurred. Once the product passes quality control, it is sent through final filtration before packaging. Fine mesh inline filters remove any particulate matter that may have formed during cooking or cooling. This ensures a perfectly smooth syrup with no grit or undissolved solids. Packaging Hershey's syrup involves a highly synchronized series of steps designed for both hygiene and speed. The most common containers are squeezable plastic bottles, which are blow molded from PET or HDPE on site or delivered pre-formed. These bottles are first conveyed through an air rinse system that blasts ionized air to remove dust or debris. They are then indexed into position beneath the filling nozzles. Filling is performed using servo-controlled, volumetric, or piston fillers. These machines are calibrated to deliver exact quantities of syrup, typically in the range of 650 to 800 grams per bottle, depending on size. The syrup is dispensed at controlled speeds to prevent splashing or air entrapment. No drip filling heads are often used to maintain clean bottle exteriors and reduce product waste. After filling, the bottles move to the capping station. Caps are sorted using centrifugal feeders and applied using torque-monitored capping heads, which ensure a tight seal without over-tightening. Each bottle is then passed under an induction sealer, where an aluminum foil seal is bonded to the bottle mouth using electromagnetic heating. This tamper-evident seal not only enhances shelf life, but also guarantees product integrity. Next, the bottles pass through a labeling machine where pressure-sensitive labels are applied with exacting precision. Labels include not just branding and nutrition information, but also critical traceability codes, including batch numbers, timestamps, and plant identifiers. These details are laser-etched or printed using inkjet coders. Before leaving the line, every bottle passes a series of automated inspection stations. Vision systems equipped with high-speed cameras check for correct fill levels, cap placement, seal integrity, and label alignment. Any non-conforming product is rejected and diverted to a separate inspection area for manual review. Approved bottles are grouped into cartons or shrink-wrapped multi-packs. Robotic case packers load the bottles into boxes, which are then sealed, labeled, and palletized. These pallets are stretch-wrapped and tagged with scannable barcodes for warehouse tracking. The entire process from filling to palletization is fully integrated into Hershey's manufacturing execution system, allowing for real-time monitoring and inventory control. Palletized syrup is transported to climate-controlled distribution centers. While Hershey's syrup is shelf-stable, temperature extremes can still impact viscosity and appearance. Warehouses maintain stable conditions to prevent thickening in cold weather or oil separation in high heat. From there, the product is dispatched to retail partners, online fulfillment centers, and export destinations. Throughout the supply chain, Hershey's implements strict food safety protocols, including compliance with the Global Food Safety Initiative, hazard analysis and critical control points, and FDA regulations. Traceability is maintained from raw cocoa bean to finished bottle, ensuring any issue can be traced and contained within hours. What makes Hershey's syrup so enduring in the marketplace isn't just its flavor, it's the precision and consistency made possible through modern food engineering. Every step of the process, from the aggressive mixing of cocoa powder to the final induction seal, is executed with scientific rigor. Equipment calibration, ingredient testing, and continuous improvement protocols ensure that each bottle tastes the same, pours the same, and satisfies the same cravings generation after generation. As the brand moves forward, sustainability is becoming an even greater focus. Efforts to reduce plastic use in packaging, improve energy efficiency in heating and cooling systems, and source more ethical cocoa are all part of Hershey's long-term production goals. Some lines are exploring bio-based PET alternatives for bottles and increasing recycling within plant operations. Continuous feedback from quality assurance teams and customer satisfaction metrics are used to refine processing parameters and optimize flavor retention across product shelf life. The production of Toblerone begins with the sourcing and preparation of its raw ingredients. The main base is Swiss milk chocolate, which itself is composed of cocoa beans, sugar, milk powder, cocoa butter, and a small amount of emulsifier to control texture and stability. Cocoa beans are harvested in equatorial regions such as West Africa, Central and South America, and parts of Asia. These beans are fermented, dried, shipped, and roasted before they ever arrive at the Toblerone factory. Once in Switzerland, the beans are roasted in large rotating drum roasters that allow precise control over temperature and time, coaxing out the flavor precursors that give chocolate its complexity. After roasting, the beans are cracked and winnowed in specialized machines that separate the outer husk from the valuable nib. These nibs are then ground in heavy-duty industrial mills until they form a thick liquid mass known as cocoa liquor. From this base, two critical components can be separated under pressure: cocoa butter, which provides smoothness and melt, and cocoa solids, which supply chocolate's intense flavor and color. Both of these fractions will later be recombined in the desired ratio. The sugar used in Toblerone typically comes from sugar beet grown across Europe or sugarcane imported from other regions. The sugar is refined to an ultra-fine powder because chocolate manufacturing requires extremely small particle sizes to create a smooth, melt-in-the-mouth sensation. The milk used for Toblerone is collected fresh from Swiss dairies, dried into powdered form through spray drying towers, and tested for purity, flavor, and fat content. Milk powder is a crucial element that lends Swiss chocolate its creamy, delicate profile. In addition to milk chocolate, Toblerone contains honey and almond nougat, which must also be manufactured with precision. The nougat is produced by mixing ground almonds, sugar, egg white, and honey, which are cooked to a stable yet chewy consistency. This nougat is then cooled, solidified, and broken down into small, crunchy pieces that can later be blended with chocolate. To achieve the consistent particle size required, nougat fragments are milled in special grinding machines and screened through sieves to ensure no overly large chunks remain. These pieces must be uniform so that every bite of a Toblerone bar has the same texture. Once all the raw materials are prepared, the actual chocolate making begins. In the mixing phase, cocoa liquor, cocoa butter, milk powder, sugar, and emulsifiers are blended in large stainless steel vats equipped with heavy-duty paddles. The proportions are carefully controlled by automated dosing systems linked to computerized recipes. At this stage, the nougat and honey are not yet introduced because the base chocolate must first go through refining and conching processes to achieve the correct texture. The mixed chocolate is passed through a series of 5-roll refiners, massive machines with rollers set at progressively tighter gaps. This action grinds the solid particles down to around 20 microns in size, small enough that the tongue cannot detect any graininess. After refining, the powdered chocolate mass is placed into conches, large trough-like machines fitted with rotating arms that knead, aerate, and heat the mixture. Conching can last from several hours to over a day, depending on the desired flavor development. During this time, volatile acids are driven off. The particles become evenly coated with fat, and the chocolate develops its characteristic smoothness and balanced flavor. Only after the conching process is complete are the honey and nougat pieces gently incorporated. This timing ensures that the delicate flavors of honey remain intact and that nougat pieces maintain their crunch without being broken down by extended mechanical agitation. Once the full mixture is ready, the chocolate must be tempered. Tempering is an essential process in chocolate manufacturing because cocoa butter can crystallize in several different forms, some of which produce dull, crumbly chocolate rather than glossy, snappy bars. In industrial tempering machines, the chocolate mass is cooled and reheated in a controlled sequence so that the stable form of cocoa butter crystals dominates. This process ensures that Toblerone has a shiny surface, a crisp snap, and does not melt prematurely during storage. With the chocolate tempered, the forming process begins. Unlike standard chocolate bars, Toblerone requires specialized molds shaped into its iconic triangular peaks. These molds are usually made from polycarbonate or food-grade stainless steel. Tempered chocolate with embedded nougat pieces is pumped into the molds using automated depositor heads that fill each cavity with the precise amount of chocolate. To ensure the chocolate fully fills the peaks and valleys, the molds are vibrated mechanically, which releases trapped air bubbles and distributes the mixture evenly. The filled molds then travel along a cooling tunnel, a long conveyor housed in a refrigerated chamber where controlled airflow brings the chocolate down to a stable temperature and solidifies it without causing surface defects. Once cooled and hardened, the bars are removed from the molds by automated demolding machines that gently flex or tap the molds to release the chocolate. These freshly formed Toblerone bars are now ready for packaging, but before that, they undergo stringent quality checks. Automated vision systems scan each bar for surface defects, broken peaks, or air holes, while weight sensors confirm that each bar meets precise specifications. Samples are also tested in quality control laboratories, where technicians measure fat content, melting behavior, and flavor consistency against reference standards. Packaging Toblerone presents another interesting challenge because of its shape. The triangular bar requires a distinctive triangular prism carton, which has become as iconic as the chocolate itself. In the factory, automated carton forming machines fold and glue flat cardboard blanks into their three-dimensional prism shapes. Meanwhile, chocolate bars are wrapped in foil or paper to preserve freshness and protect them from contamination. Robotic arms then insert the wrapped bars into the triangular cartons at high speed. High-resolution printers add branding, logos, nutritional information, and batch codes directly onto the cartons. Sealed cartons are checked once again by sensors to ensure proper closure before being loaded into larger shipping cases. The packaged Toblerone bars are stacked onto pallets using automated palletizing systems. From here, they are transferred into climate-controlled warehouses where temperature and humidity are carefully maintained to prevent bloom or texture loss. Distribution logistics then take over, with pallets loaded onto trucks, trains, or containers for shipment worldwide. Throughout transport, maintaining cool and dry conditions is essential since chocolate is sensitive to fluctuations that can cause whitening or melting. Retailers ultimately receive the bars, place them on shelves, and consumers across the globe recognize them instantly by their unique triangular boxes. Beyond the mechanics, the production of Toblerone highlights the integration of tradition and technology. The recipe remains faithful to its early 20th century origins, with Swiss milk chocolate, honey, and nougat at the core. Yet the scale, precision, and automation in today's factories allow millions of identical bars to be produced annually. Every piece of equipment, from conches to molding lines, is designed to ensure consistency and quality on a massive scale while still protecting the integrity of the original idea. The story of Ferrero Rocher begins in Italy, where the Ferrero company, already famous for products such as Nutella, Kinder chocolates, and Tic Tacs, sought to create a premium confection that combined texture, flavor, and an elegant presentation. Introduced in the 1980s, Ferrero Rocher quickly became a global success, celebrated both for its taste and for the distinctive gold-wrapped packaging that evoked luxury and indulgence. The brand capitalized on the image of a special occasion treat, often presented in clear plastic boxes as a gift rather than consumed casually, like standard candy bars. Behind this seemingly simple product lies a surprisingly complex and carefully engineered manufacturing process. The core of Ferrero Rocher is the hazelnut. Hazelnuts are grown primarily in Turkey, Italy, and other temperate regions, and Ferrero is one of the largest global purchasers of this nut. Quality control begins right at the source. Hazelnuts are harvested, sorted, and dried, then shipped to processing facilities where they are tested for size, flavor, and absence of defects. At the factory, the nuts are roasted in large drum or fluidized bed roasters, a step that enhances their flavor by developing nutty, caramelized notes while also reducing moisture content. Automated systems monitor roasting temperature and time to ensure uniform results, since even slight variations can affect flavor consistency. Once roasted, the hazelnuts are cooled, stored under controlled humidity, and eventually fed into the production lines. Each Ferrero Rocher chocolate begins with a single whole hazelnut, which forms the central core of the confection. Hazelnuts destined for the center are inspected once more to ensure they are intact and properly sized. These nuts are then aligned and portioned using vibratory feeders and precision dispensers so that each chocolate receives one whole hazelnut without exception. Surrounding the hazelnut core is a thin, delicate layer of chocolate cream. This filling is essentially a version of hazelnut praline, a paste made by grinding roasted hazelnuts with sugar and blending it with cocoa powder and vegetable fats to achieve a smooth, creamy texture. The cream is manufactured in large mixing tanks fitted with high shear blades to homogenize the mixture. Precise dosing pumps then deliver just the right amount of this cream around each hazelnut, creating the first layer of indulgence. Automated forming systems encase the nut with cream by depositing the filling into hemispherical molds, placing a nut inside and capping it with more cream, producing a complete sphere with the nut suspended at its center. Once this creamy core has been formed, it is encased within a thin, crisp wafer shell. This is one of the most technically intriguing steps of Ferrero Rocher production. Wafer batter, made from wheat flour, water, and small amounts of oil or sugar, is prepared in large mixing vats, then deposited into heated wafer presses. These presses work much like industrial waffle irons, forming thin sheets of crispy wafer by baking at high temperatures until golden and brittle. The baked sheets are then trimmed and conveyed to shaping stations, where specialized machines stamp out hemispherical wafer cups. Each cream-filled hazelnut core is placed into one of these wafer cups, and a second wafer half is pressed onto the top, sealing the sphere. The result is a delicate, hollow wafer shell encapsulating the nut and cream filling. Excess wafer edges are carefully trimmed away by automated cutters to create a smooth, uniform sphere. At this point, the confection still lacks its outer chocolate and hazelnut coating. To prepare for this stage, the wafer balls are conveyed through enrobing lines. The first step involves a curtain of liquid milk chocolate through which the spheres pass, ensuring complete coverage. This coating acts both as a sealant to protect the wafer from moisture and as the base layer for the final crunchy coating. The chocolate used here is formulated specifically to achieve the right viscosity for enrobing. Too thin, and it would not provide adequate coverage. Too thick, and it would result in an uneven or clumpy surface. Immediately after being enrobed, the wet chocolate surface of the spheres is showered with finely chopped, roasted hazelnut pieces. These pieces are produced in the same factory by grinding roasted hazelnuts into small fragments using hammer mills and screening them to the desired particle size. Precision vibratory feeders sprinkle these fragments onto the freshly coated spheres, where they stick to the chocolate layer. The timing is critical. The nuts must adhere firmly before the chocolate begins to set. Once fully coated, the spheres pass through a second chocolate enrobing stage that seals the nut pieces into place, creating the distinctive rough, textured surface of Ferrero Rocher. The enrobed chocolates then enter a cooling tunnel, a long, refrigerated conveyor that gradually reduces the temperature of the product in controlled stages. Rapid cooling can cause cracks or fat bloom, so the temperature and airflow are carefully regulated to solidify the chocolate smoothly. By the time the spheres emerge from the tunnel, they are fully set and ready for packaging. Packaging is a vital part of Ferrero Rocher's appeal. The chocolates are wrapped individually in thin gold foil, which not only provides protection but also conveys a sense of elegance and exclusivity. Automated wrapping machines handle this delicate process. Each chocolate is positioned precisely on a sheet of foil, after which mechanical fingers fold and twist the foil snugly around the sphere. The top of the chocolate is decorated with a small circular label bearing the Ferrero Rocher logo. The wrapped chocolates are then placed into pleated brown paper cups that provide structural support and enhance the presentation. Once wrapped and cupped, the chocolates are arranged in their signature clear plastic boxes, often in patterns that maximize both aesthetics and space efficiency. Robotic arms or high-speed pick-and-place machines handle this task with great precision, ensuring that the chocolates are not damaged during packing. Lids are sealed onto the boxes, and decorative labels and logos are applied. These boxes are then grouped into larger cartons for transport and distribution. Throughout the entire process, stringent quality control measures are in place. Samples are taken at every stage to check for weight, size, flavor, and texture. Advanced vision inspection systems ensure that no product leaves the line with missing coatings, broken shells, or defective wrapping. Hazard control protocols are enforced under HACCP guidelines, with metal detectors and X-ray scanners checking for contaminants. Since hazelnuts are allergenic, factories maintain strict segregation and cleaning practices to avoid cross-contamination with other product lines. Storage and distribution of Ferrero Rocher also require careful attention. Chocolate products are sensitive to heat and humidity, which can cause melting, sugar bloom, or fat bloom. Factories and warehouses maintain controlled conditions of around 18 to 20 degrees Celsius with low humidity. From the warehouse, products are shipped worldwide by truck, container, or air freight, depending on demand and destination. Cold chain logistics ensure that chocolates arrive at retailers in pristine condition. What makes Ferrero Rocher remarkable is how its production combines advanced industrial automation with the appearance of artisanal craftsmanship. Each piece feels handmade because of its individual wrapping and layered textures, yet in reality, every step is driven by highly specialized machinery capable of producing thousands of chocolates per hour. The golden foil, the delicate paper cup, the precision placement in plastic boxes, all of these details contribute to the perception of luxury, but they are achieved through meticulously engineered automation. The success of Ferrero Rocher also lies in the balance of textures created by the layered construction. The crunch of the outer hazelnut-coated chocolate shell gives way to the light crispness of the wafer, followed by the smooth, creamy praline, and finally, the whole roasted hazelnut at the center. Each of these elements requires different processing conditions, yet they must come together in perfect harmony in every piece. Achieving this consistently across millions of units each day is a testament to the sophistication of modern confectionery engineering. The story begins with sourcing the most important ingredient of all, the cocoa bean. Lindt maintains strict control over the origins of its cocoa supply, working directly with farming communities in West Africa, Central and South America, and other equatorial regions. Cocoa trees bear pods that are harvested, split open, and filled with cocoa beans surrounded by pulp. These beans are fermented in large piles or boxes covered with banana leaves to trap heat, where natural yeasts and bacteria convert sugars into acids that develop the characteristic chocolate flavor precursors. After several days of fermentation, the beans are dried in the sun to reduce their moisture content before being bagged and shipped overseas to Europe. Once the cocoa beans arrive at Lindt's factories, quality control is paramount. Samples are taken from each batch and roasted in laboratory test roasters to evaluate flavor potential. Beans are graded for size, moisture, aroma, and absence of defects. Only the best lots are accepted into production. The accepted beans are then cleaned to remove debris such as dust, stones, or fibers before entering the roasting stage. In industrial-scale drum roasters, the beans are heated at carefully controlled temperatures that coax out the complex flavors. Roasting is one of the most critical steps as it defines the final taste profile. Too light, and the chocolate will be weak and acidic. Too dark, and it may become bitter or burnt. After roasting, the beans are cracked open in specialized breaking machines. These machines use a combination of rollers and air separation to break the beans into nibs while blowing away the lighter husks. The nibs are the true treasure, composed of cocoa solids and cocoa butter. They are then ground in massive stone or steel mills until they release their fat and form a thick, dark liquid known as cocoa liquor. This liquor can either be used directly in chocolate or pressed hydraulically to separate it into cocoa butter, the fat component, and cocoa solids, which are later milled into cocoa powder. Milk and sugar are the next essential components of Lindt's milk chocolate products. Fresh milk from Swiss dairies is delivered and processed into milk powder using spray drying technology. Sugar, usually sourced from European sugar beets or imported cane sugar, is refined to an extremely fine crystal size. The cocoa liquor, cocoa butter, milk powder, and sugar are combined in large stainless steel mixers. At this stage, the mixture is still coarse and granular. To create the silky smoothness for which Lindt is renowned, it must undergo refining. Refining occurs in 5-roll mills, towering machines equipped with rollers that are set progressively closer together. The chocolate mass passes through each roller gap, which crushes the sugar and cocoa particles smaller and smaller until they reach a size of about 20 microns. This is smaller than the sensitivity of the tongue, so the final chocolate feels smooth and creamy instead of gritty. The finely ground mass is then ready for the process that made Lindt famous, conching. Conching is the heart of Lindt chocolate production. Originally, Rodolphe Lindt developed the technique by accident, leaving his mixer running over the weekend. The result was a chocolate with unprecedented smoothness and richness. In modern factories, conching is carried out in massive steel troughs with rotating arms that knead, agitate, and aerate the chocolate mass for hours or even days. During this time, volatile acids are evaporated, particles are coated with cocoa butter, and the mass becomes fluid and homogeneous. The friction of the conching arms generates heat, which helps drive off unwanted flavors and develops a balanced, mellow profile. Different Lindt products undergo different durations of conching, giving rise to the nuanced flavor differences across their range. Once the chocolate has been conched to perfection, it must be tempered. Cocoa butter is a polymorphic fat, meaning it can crystallize in several different forms. Only one of these forms, known as the stable beta crystal, gives chocolate its glossy sheen, sharp snap, and resistance to bloom. Industrial tempering machines cool and reheat the chocolate in carefully controlled steps, encouraging only the stable crystal form to develop. This process requires absolute precision, as improper tempering can ruin the texture and appearance of the final chocolate. After tempering, the chocolate is ready to be formed into products. For standard chocolate bars, the tempered chocolate is pumped into polycarbonate molds, shaped according to Lindt's signature designs. The molds, pass through vibrating stations that remove air bubbles and ensure an even fill. They then travel along cooling tunnels where controlled airflow and refrigeration gradually solidify the chocolate. Once hardened, the bars are ejected from the molds by mechanical tapping or flexing, inspected for defects, and transferred to packaging lines. For Lindt's famous Lindor truffles, the process is more intricate. These confections feature a delicate chocolate shell that encloses a smooth, flowing filling. The shell is created by spinning tempered chocolate inside spherical molds, forming a thin but strong layer. Once the shells are hardened, a liquid filling made of chocolate blended with additional cocoa butter and sometimes cream is injected into the center. The spheres are sealed with more chocolate and cooled again to set. When consumers bite into a Lindor truffle, the outer shell gives way to the luxuriously melting filling, a sensation created through meticulous engineering. After molding, forming, or enrobing, packaging becomes the next crucial stage. Lindt bars are wrapped in foil and paper sleeves that maintain freshness while presenting a premium look. Lindor truffles are individually wrapped in colored foils, twisted at the ends to create an elegant presentation. Automated wrapping machines perform this at high speed while ensuring consistency. The wrapped chocolates are then boxed, labeled, and grouped into cartons for shipping. Each package bears batch codes for traceability, and automated vision systems check alignment and sealing before boxes leave the factory. Throughout the entire process, quality control is relentless. Every batch of cocoa liquor is tasted and analyzed for flavor balance. Samples of conched chocolate are tested for viscosity, fat content, and particle size. Finished products are checked for gloss, snap, and uniformity. Food safety is upheld through rigorous hygiene protocols, allergen control, and HACCP systems. Metal detectors and X-ray scanners ensure that no foreign objects contaminate the products. Distribution is the final step in Lindt Chocolate's journey. Products are stored in climate-controlled warehouses where temperature and humidity are carefully monitored to prevent bloom or melting. From there, chocolates are shipped worldwide in refrigerated containers or trucks. Retailers receive them in pristine condition, and consumers encounter them either in Lindt boutiques, luxury stores, supermarkets, or duty-free shops across the globe. What sets Lindt apart from many other chocolate manufacturers is its combination of historical craftsmanship and cutting-edge automation. The conching process, pioneered by Rodolphe Lindt, remains central, yet the scale has grown to thousands of tons per year. Sophisticated dosing systems, computer-controlled tempering units, and robotic packaging lines ensure absolute consistency, while the company's commitment to quality and sourcing upholds its reputation. The result is chocolate that tastes handmade, yet is produced in enormous quantities. Krispy Kreme uses a proprietary blend of enriched wheat flour, one formulated specifically for its lightness, protein balance, and ability to yield that signature fluffy bite. The flour is sourced from select mills that maintain tight quality control standards, ensuring the particle size, protein content, and gluten strength all fall within strict tolerances. Once delivered to the facility, the flour is stored in stainless steel silos under controlled temperature and humidity, preventing clumping and spoilage. Next, there's yeast, the biological engine behind the dough's rise. Krispy Kreme uses a commercial strain of baker's yeast known for its rapid activation, consistent fermentation profile, and neutral flavor. The yeast is usually delivered in refrigerated blocks or vacuum-sealed pouches to ensure maximum viability. Alongside the yeast, the other raw ingredients include non-fat dry milk powder, high-stability vegetable shortening, dextrose, salt, and water. Each of these ingredients plays a crucial role in shaping the final taste and texture of the donut. The shortening provides mouthfeel and moisture retention, while the dry milk lends a creamy undertone and enhances browning during frying. In the mixing phase, the ingredients are loaded into a spiral or planetary industrial mixer. The water is typically warmed to around 95 to 105 degrees Celsius before being introduced to activate the yeast. The mixer operates on a timed cycle, first gently combining the dry and wet components, then increasing speed to develop gluten and build dough structure. The dough is mixed until it achieves a smooth, elastic consistency with careful monitoring of temperature and hydration levels. If the dough becomes too warm, it risks overproofing, too cold, and fermentation is delayed. Sensors in the mixing bowl monitor the dough's internal temperature, moisture content, and even CO2 output to ensure consistency. Once the dough is formed, it enters the bulk fermentation phase. Giant stainless steel troughs, called dough rests, hold the dough as it ferments for the first time. During this period, the yeast metabolizes sugars and starches, producing carbon dioxide and ethanol. This expands the dough and begins developing its light, spongy structure. Krispy Kreme controls this step precisely, maintaining a temperature of around 80 degrees and 85% relative humidity in the proofing room. The dough rests here for approximately 30 to 40 minutes, depending on the batch size and ambient conditions. After bulk fermentation, the dough is transferred to a sheeting system. This is where things start to get visually impressive. The dough is rolled and flattened by calibrated rollers until it reaches a uniform thickness, typically between 10 to 12 millimeters. From here, it enters the cutting stage. A rotary die cutter stamps out perfect donut rings and holes in a continuous, automated process. The cutting dies are precision machined from stainless steel to ensure sharp, clean cuts and minimal dough waste. Any scrap dough is immediately collected by conveyors and reintroduced into the mixing system for reuse. Each donut ring now travels along a conveyor to the second proofing chamber, essentially a gigantic, climate-controlled cabinet lined with slow-moving racks. Inside, the donuts undergo their final proof, where they double in size due to continued yeast activity. The environment here is tightly regulated, around 90 degrees here and nearly 85% humidity. This proofing process typically lasts 30 minutes, but sensors embedded in the chamber walls adjust for ambient shifts in temperature or humidity, ensuring each donut achieves the perfect rise. Now comes one of the most mesmerizing parts of the process, the fry line. The fully proofed donuts are gently deposited into a continuous flow fryer using an overhead lifting mechanism that preserves their delicate structure. The frying oil, usually a high stability palm or soybean blend, is maintained at a precise temperature of approximately 365 degrees. Each donut floats along the surface, first frying one side, then automatically flipping at the midpoint using a mechanical turner. This results in the even golden brown exterior Krispy Kreme is known for, with a pale proof line around the center indicating proper fermentation. The frying process takes just under a minute per side, and the timing is crucial. Over-frying results in a dense, oily product. Under-frying leaves it doughy and structurally unsound. Oil filtration systems continuously clean and circulate the frying oil, removing carbonized particles and extending the oil's life while maintaining food safety. Once the donuts exit the fryer, they move onto a draining conveyor where excess oil drips away. The donuts are now fully cooked, but they're still bare, until they pass through the glaze waterfall. This is the stage most visitors at Krispy Kreme stores eagerly watch through the viewing window. The glaze itself is a proprietary blend of confectioner's sugar, water, and stabilizers, mixed in large heated vats to maintain fluidity. It's heated to a precise temperature to ensure it flows evenly over the donuts without soaking them. As the donuts travel beneath the waterfall, a curtain of glaze coats their entire surface in one smooth motion. The donuts continue to move along the belt for several feet to allow the glaze to set. During this time, cooling fans blow across the surface to speed up the crystallization process, giving the glaze its characteristic sheen and snap. At this stage, the original glazed donuts are complete, but not all donuts stop here. Many are diverted down alternate lines for filling, topping, or decoration. Filled varieties like custard, jelly, or cream-filled donuts are processed using pneumatic injection stations. The donuts are gripped and punctured automatically, and then a precise quantity of filling is injected into each center using calibrated nozzles. Topping lines include various enrobing stations for chocolate dips, icing drizzles, and even cookie crumb coatings, depending on the product line. Once decorated, the donuts pass through a final quality control checkpoint. Here, high-speed cameras, sensors, and human inspectors work in tandem to identify deformities, glaze coverage issues, or structural flaws. Any donut that doesn't meet the company's stringent standards is diverted and discarded or sent for animal feed, depending on local regulations. Now comes the packaging process. Original glazed donuts are usually arranged by robotic arms into branded trays or boxes, depending on the sales channel, whether destined for in-store display, grocery retail, or food service distribution. Boxes are barcoded, date-stamped, and sealed automatically. For freshness, Krispy Kreme relies on just-in-time manufacturing. Many facilities bake and ship multiple times per day, with some outlets even co-located within the production plant itself to reduce handling and delay. For external distribution, the boxed donuts are loaded into climate-controlled trucks equipped with racking systems that prevent damage during transit. These trucks make scheduled routes to retail locations, grocery partners, and kiosk outlets, often arriving just hours after the donuts were made. Once on site, employees stock the shelves or display racks, ensuring the donuts are sold within their optimal freshness window, typically less than 24 hours. Meanwhile, any donuts not sold by the end of the day are generally removed to preserve Krispy Kreme's reputation for freshness. In some regions, unsold inventory is donated to food banks or repurposed, while others adhere to strict disposal policies. Throughout this entire process, automation and precision engineering play a central role. From programmable logic controllers managing the mixing and proofing cycles, to machine vision systems inspecting glaze coverage, every step is optimized for consistency, safety, and speed. The machinery involved is custom designed, often proprietary, and requires teams of trained technicians to maintain. Clean-in-place systems are installed throughout the facility to sanitize pipes, mixers, glaze troughs, and conveyors between production runs. This minimizes downtime while ensuring compliance with food safety regulations. Every aspect, from microbial swab testing to allergen control and traceability, is monitored via centralized software platforms, which can track each batch of donuts from flour silo to store shelf. The story of every M&M starts with one essential component: chocolate. The heart of a standard M&M is a solid drop of milk chocolate, though other varieties, like peanut, almond, crispy, pretzel, or peanut butter, feature different cores. But regardless of the variety, the production begins in the chocolate refining department, where raw ingredients such as cocoa liquor, cocoa butter, sugar, and milk solids are blended to make a smooth, consistent chocolate base. The chocolate used in M&Ms is tailored for firmness and melt resistance, specifically engineered to maintain its structure during the coating process. Large stainless steel tanks are used to melt and hold the chocolate at controlled temperatures. Automated valves and mixers regulate temperature, viscosity, and flow characteristics. Chocolate destined for M&M production must be carefully refined to reduce particle size, usually to around 20 microns. This is done in multiple stages using equipment like ball mills, roller refiners, and conchas. These machines apply friction, pressure, and shear force to break down the solid particles until the chocolate achieves its desired mouthfeel. Once refined, the chocolate is pumped to depositors, automated nozzles that precisely dispense the liquid chocolate into molds or droplet-forming equipment. For the classic M&Ms, the chocolate is dropped onto a cool, rotating belt in small, round portions, forming button-shaped discs. These droplets are cooled rapidly using chilled air tunnels to harden them before further processing. The cooled chocolate centers are then collected and sent to the coating drums. These are large rotating pans, sometimes referred to as dragees pans or coating kettles, where the hard candy shell is gradually built around the chocolate core. This is the heart of the M&M production process and one of the most visually striking steps in the factory. The coating process is a slow and incremental buildup, achieved by spraying a fine mist of sugar syrup onto the tumbling chocolate centers, then drying and hardening that layer before repeating the cycle. Each coating drum can hold hundreds of thousands of chocolate centers at once. As the drum rotates, a fine spray of syrup, consisting mainly of sugar and water with optional corn syrup, is applied in short bursts. Warm air is then blown into the drum to dry the layer, allowing the sugar to crystallize into a thin, hard shell. This cycle is repeated dozens of times, each time adding a microscopically thin layer to build up the final shell thickness. Over time, this layering transforms the centers from soft chocolate buttons to perfectly round, hard-shelled candies. During this stage, technicians monitor coating uniformity, size consistency, and drying times using high-speed cameras and inline sensors. If the temperature or humidity in the coating room deviates too far from spec, it can ruin an entire batch, leading to shell cracking or poor adhesion. Once the desired shell thickness is achieved, the M&Ms are polished to give them their signature shine. This is done by adding polishing agents, such as carnauba wax or beeswax, to the coating drum in very small amounts. These natural food-grade waxes help create a glossy finish that not only enhances visual appeal, but also helps prevent sticking and moisture absorption during storage. The polishing phase takes less time than coating, but must be precisely timed to avoid overwaxing, which can result in a greasy or smeared appearance. The next step is color application, which may seem simple, but is, in fact, a carefully controlled phase. M&Ms come in a variety of colors, typically red, orange, yellow, green, blue, and brown. The color coding is applied using a sugar-based dye solution, sprayed in another round of layering inside rotating pans. Each batch is divided according to how many of each color are required. Food-grade colorants are mixed with water and a binding agent to ensure even adherence to the existing shell. After the colorant is applied, warm air is used to dry the layer, and another wax polish may be added to lock in the color and maintain shine. The factory uses precise batch tracking and automated scheduling software to ensure the correct number of each color is produced. For example, if red accounts for 20% of a standard bag's color distribution, the system ensures exactly that percentage is created during the run. This attention to detail keeps the consumer experience consistent across bags, boxes, and geographic regions. After color coding, the candies proceed to the printing station, where the iconic M is stamped on each piece. This is accomplished using high-speed, food-safe ink printers. The M&Ms are gently vibrated into a single layer on a moving conveyor belt that aligns them properly for stamping. The white edible ink is applied using a flexographic or offset stamping mechanism that imprints the M logo without damaging the candy's surface. To ensure accuracy, machine vision systems monitor the printing in real time, checking for clarity, alignment, and completeness. Any candies that are misprinted or blank may be removed by pneumatic air jets and diverted for recycling or reprocessing. Now the M&Ms are ready for packaging. This phase of production involves a combination of robotics, weight-checking systems, and packaging machinery that operates at astonishing speeds. The candies are directed into vertical form-fill-seal machines or horizontal flow wrappers, depending on the packaging format. Multi-head weighers dispense precise quantities of M&Ms into each bag or pouch, ensuring weight compliance to legal standards. The packaging film is heat-sealed to form a tamper-evident, airtight barrier that preserves freshness and extends shelf life. For bulk formats, such as large tubs, party-sized bags, or vending packs, the process is slightly different but still highly automated. The machines are programmed to handle various product sizes, materials, and pack types without compromising accuracy. Barcodes, expiration dates, and lot numbers are printed onto each package to allow for traceability. Once packaged, the products are conveyed to case packing robots, which group them into cartons or boxes for shipping. These cases are then sealed, palletized by robotic arms, and shrink-wrapped for transport. Pallets are stored temporarily in climate-controlled warehouses before being loaded onto distribution trucks that carry them to retail centers, convenience stores, vending machine suppliers, and international shipping hubs. Throughout the entire process, food safety and quality control are paramount. The factory floor is governed by strict hygiene protocols. employees are required to wear sanitary gear, and the equipment is sanitized regularly using automated clean-in-place systems. Random sampling is conducted at every critical control point, from chocolate refining to shell thickness to final packaging. Laboratory testing checks for microbial contamination, allergen presence, and chemical composition. Quality assurance teams also perform taste tests, structural integrity tests, and heat resistance trials to ensure the product meets Mars Inc.'s global standards. In the case of peanut or almond M&Ms, the process is similar but begins with nut preparation. Peanuts, for instance, are roasted in-house to develop their flavor and reduce microbial load. They are then cooled, sorted by size, and coated in a preliminary layer of chocolate before undergoing the same sugar shell layering process. Their irregular shape requires adjustments to coating speed and rotation patterns to ensure even coverage. The engineering behind M&M production is not only a marvel of food science, but also a study in high-speed manufacturing. Thousands of M&Ms can be produced every minute, yet each one must look and taste exactly the same. This requires the coordination of multiple disciplines: mechanical engineering, chemistry, automation, logistics, and sensory evaluation. The process begins not with whole potatoes, but with dehydrated potato flakes and potato starch. These form the base of the Pringles dough. The flakes are manufactured off-site through a separate drying process where peeled, cooked potatoes are mashed and then passed through drum dryers to remove water, creating thin, crisp sheets of dried potato. These are ground into fine granules and delivered to Pringles production facilities in bulk quantities, stored in climate-controlled silos to maintain moisture levels and prevent clumping. To this potato base, manufacturers add a precise blend of rice flour, corn flour, and wheat starch. This multi-starch formula gives Pringles their distinctive light, yet durable crunch, firmer than a classic chip, but less dense than a cracker. Each ingredient is selected for its functional properties. Rice flour contributes to lightness and reduces oil absorption. Corn flour provides structure and contributes to the crisp texture. Wheat starch acts as a binding agent and helps form the dough into a cohesive sheet. Inside the factory, these dry ingredients are metered into high-capacity industrial mixers. Water is added gradually, and the mixture is agitated until a cohesive dough forms. The consistency of the dough is critical. It must be pliable enough to be rolled and shaped, yet stiff enough to hold its form during frying. Too much water would cause the crisps to bubble and deform. Too little, and they would crack or crumble during processing. After mixing, the dough is conveyed onto a series of steel rollers in a sheeting machine. These rollers press the dough into a continuous, thin sheet, typically about 0.7 to 1 millimeter thick. The uniformity of this sheet is crucial, as even slight thickness variations can affect how the chips fry, blister, and brown. Advanced sensors mounted near the rollers continuously monitor sheet thickness, feeding data to the control system, which makes micro adjustments in real time. Next, the sheeted dough passes under a rotary die cutter. This is a cylindrical cutter with thousands of identically shaped molds engraved into its surface. As the sheet moves beneath it, the die cuts out dozens of curved oval crisps at a time, each one precisely measured to match Pringles' iconic dimensions, around 6.5 centimeters long and 5.5 centimeters wide, shaped with a unique double-curved profile known as a hyperbolic paraboloid. This mathematical shape isn't just aesthetic, it offers stackability, strength, and an audible crunch due to its uniform stress distribution. The dough scrap that remains between the cutouts is immediately separated and returned to the beginning of the process. Conveyor belts collect and transport the unused dough back to the mixer, where it is reincorporated into fresh dough. This closed-loop system minimizes waste and ensures efficiency in ingredient usage. Once cut, the raw crisps are gently lifted from the sheet using suction cups or air jets and placed onto a moving metal belt composed of dozens of concave molds. Each mold perfectly matches the chip's final saddle shape. This belt then moves the raw crisps into the fryer, an enormous stainless steel bath filled with hot vegetable oil, maintained at a consistent temperature of around 170 to 180 degrees. The crisps are submerged for approximately 11 seconds, long enough to remove moisture and induce a Maillard reaction, giving them their light golden brown hue and toasty flavor. Unlike traditional deep-fried potato slices that can curl, bend, or form bubbles, the Pringles molds maintain each crisp's structure during frying. Because the crisps are uniformly thin and precisely shaped, they fry evenly with no dark spots or oil saturation. Excess oil is quickly removed as the crisps exit the fryer and pass over a series of vibrating conveyors and air knives, high-pressure jets that blow away any surface oil or crumbs. At this point, the freshly fried crisps are hot, dry, and unseasoned. They move into the seasoning tunnel, a long, rotating drum equipped with sprinklers or spray nozzles. Here, flavor powders, ranging from classic original to sour cream and onion, cheddar cheese, or barbecue, are evenly applied as the crisps tumble and rotate. The flavor powders are formulated to stick to the crisp's surface via residual oil left from frying. In some varieties, additional ingredients such as powdered cheese or dehydrated vegetables are included in the seasoning blends. To prevent flavor loss and preserve freshness, the seasoned crisps are quickly cooled using forced air systems before entering the packaging phase. This cooling is critical. If the crisps are too warm, condensation can form inside the package, leading to soggy chips and microbial risk. Once cooled, they are conveyed to the stacking and canning line. This is where another defining feature of Pringles becomes prominent: their tubular canister. The stacking machine uses a system of synchronized mechanical arms, optical sensors, and robotic paddles to stack crisps one by one into perfectly aligned columns. This process is remarkably fast and precise. A sensor verifies each crisp's shape and orientation before it's inserted into the growing stack. Once a full stack reaches the correct height, typically around 80 to 100 crisps, depending on the packaging size, it is inserted vertically into a cardboard can that's been pre-formed and lined with a metallized film to prevent oil seepage and moisture intrusion. Each can is equipped with a plastic bottom, which is ultrasonically welded or heat sealed in place before filling. After the crisps are inserted, a foil lid is applied and hermetically sealed using induction heat or pressure bonding to ensure an airtight closure. A plastic snap-on cap is then placed on top, providing resealability for consumer convenience. The filled cans are then labeled and date-coded. Each can receives a printed batch number and expiration date to ensure traceability throughout the distribution chain. Vision inspection systems scan each can to ensure it is filled to the correct level, sealed properly, and free of any external defects like dents or mislabeling. Cans are grouped into multi-packs or cartons by robotic arms and placed on pallets for storage or shipment. Depending on demand and product line complexity, different varieties of Pringles may be produced in separate production runs on the same line, requiring quick and thorough cleanouts between batches to prevent flavor cross-contamination. From here, Pringles are shipped to distribution centers, retailers, and convenience stores across the globe. Thanks to the uniform shape and rigid packaging, they travel exceptionally well, with minimal breakage compared to traditional bagged chips. This durability, coupled with the brand's distinct identity, has made Pringles a staple in global snack markets. Sanitation and quality control are central throughout the process. Each stage of production, from dough mixing to final packaging, is monitored by automated control systems and human operators. Random samples are collected for lab analysis to check moisture levels, oil content, seasoning distribution, and texture. Microbial testing ensures no contamination occurs during handling. Metal detectors and X-ray machines inspect each can before shipping to catch any foreign objects that may have entered the line. Allergen controls are strictly enforced, particularly when switching between varieties like original and cheddar cheese. In addition to ensuring food safety, the factory design and equipment layout support continuous cleaning. Many machines feature clean-in-place systems that pump sanitizing fluids through the equipment without requiring disassembly. Air filtration systems and positive pressure rooms minimize the risk of dust and airborne contaminants affecting product quality. Beyond the manufacturing floor, the creation of new Pringles flavors and formats involves food scientists and R&D specialists who develop seasoning blends, test mouthfeel, and conduct sensory panels with trained tasters. Innovations like Pringles Wavy or Pringles Scorchin follow the same base process, with minor adjustments in dough formulation or seasoning protocols. Despite their high-tech origin, Pringles still deliver a simple satisfaction, a crisp, flavorful bite that feels familiar and fun. But behind that enjoyment is a complex dance of precision equipment, mathematical shaping, and carefully designed formulations. From powdered potatoes to perfectly stacked crisps, every Pringle is a product not just of flavor, but of industrial ingenuity. A testament to how food science can transform something as humble as a potato into a globally recognized snack, and how Haribo gummies come to life, from raw ingredients to the finished sweet treats you love. It all starts with the base formula, the gummy candy itself. The core of every Sour Patch Kid is a soft, chewy matrix primarily composed of sugar, corn syrup, gelatin, and various fruit flavors. These ingredients must be blended in precise proportions to achieve the specific texture that Sour Patch Kids are known for. Not as firm as gummy bears, not as sticky as fruit snacks, but perfectly chewy with a fast melt in the mouth. The sugar and corn syrup form the bulk of the candy. Sugar provides structure, sweetness, and contributes to the candy's crystal clear translucence, while corn syrup prevents the sugar from recrystallizing and keeps the final product soft and elastic. These two are delivered to the factory in bulk. Sugar often in rail cars or tanker trucks, and corn syrup in heated stainless steel tankers to maintain fluidity. In the batching area of the facility, massive stainless steel mixing kettles are used to combine sugar, corn syrup, and water. The mixture is heated to dissolve the sugar and initiate cooking. Industrial mixers stir the solution constantly, while steam-jacketed walls evenly raise the temperature to around 230 degrees to 250 degrees, depending on the desired consistency and final moisture content. At this stage, the mixture is highly viscous, resembling hot, liquid sugar syrup. Once the sugar solution is properly cooked, gelatin is added. Gelatin is the key protein that gives Sour Patch Kids their elastic chew. It's derived from collagen, typically from pork or beef, and arrives at the factory as a dry powder. It is hydrated in warm water in separate tanks and added to the sugar syrup only after the syrup has cooled to an appropriate temperature to avoid denaturing the gelatin. This step transforms the hot sugar mixture into a viscoelastic candy base. At this point, citric acid and tartaric acid are introduced. These two organic acids are what provide that first intense sour kick when you bite into a Sour Patch Kid. They are used at very specific levels. Too little, and the candy loses its iconic tang. Too much, and the texture or shelf stability may be affected. Food scientists spend years perfecting this balance. In addition to acidulants, artificial and natural fruit flavorings are also added, usually concentrated solutions of compounds that mimic cherry, lemon, lime, orange, blue raspberry, and other classic flavors. Color is next. Each flavor of Sour Patch Kid is dyed with specific food-grade colorants. These are either synthetic or naturally derived, like beet juice or turmeric extract, depending on the formulation and market regulations. These colorants are added to the mix during the blending phase in tightly controlled amounts to ensure vibrancy and uniformity across batches. Once the hot candy mixture is fully mixed, it is ready to be molded. Sour Patch Kids are molded using a starch mogul system, a technique used for generations in gummy candy manufacturing. The starch mogul line begins with large trays filled with cornstarch. These trays pass under a stamping head fitted with dozens of Sour Patch Kid-shaped molds. The stamps press into the starch, forming hundreds of identical candy-shaped impressions per tray. The hot, syrupy candy mass is poured into these impressions using heated depositors. The candy flows smoothly into each cavity, forming the familiar, tiny humanoid shape. These trays, now filled with thousands of candy molds, are stacked and moved into drying rooms, also known as curing chambers. Here, the candies rest for 24 to 48 hours in warm, dry conditions. The cornstarch helps wick away moisture from the candy, allowing it to firm up without collapsing or becoming sticky. During this curing period, the gelatin sets fully, giving each candy its final chewable texture. After curing, the trays are sent to a destarching station. Here, the starch is separated from the candies using rotating sifters and vibration tables. The excess starch is collected, filtered, and reused in future molding cycles. The Sour Patch Kids, now fully formed and firm, are tumbled through gentle conveyors to remove residual starch. Now comes the most distinctive part of the process, the sour sugar coating. This is what gives Sour Patch Kids their unique mouth-watering appeal. The coating consists of a blend of fine granulated sugar, citric acid, and tartaric acid. The finished candies are placed into large rotating pans or coating drums, similar in appearance to cement mixers, but designed specifically for food products. As the drums rotate, the candies tumble over one another, while a fine mist of water or sugar solution is sprayed lightly to help the sour powder adhere. Simultaneously, the sugar acid blend is sprinkled in. The result is a uniform, crystalline coating on every piece. Timing and rotation speed are key here. Too much coating and the candy becomes overwhelming and sticky. Too little and the signature tang is lost. Factory technicians carefully monitor coating weights and perform quality checks throughout the shift to ensure product consistency. After coating, the candies are passed through a drying tunnel or cooled in ambient air to set the coating. They are then conveyed to an inspection area where cameras, sensors, and sometimes human inspectors check for shape, color, and coating uniformity. Any malformed or off-spec candies are removed from the line. Now it's time to package the final product. Sour Patch Kids are typically packed into portioned pouches, multi-serve bags, or retail cartons. The packaging line begins with form-fill-seal machines, high-speed systems that unroll printed plastic film, form it into pouches, fill each pouch with a measured weight of candy, and then seal it shut using heat. These machines are calibrated to ensure each pack contains the right amount of product and is sealed airtight for freshness. The sealed pouches are then coded with date stamps, batch numbers, and sometimes QR codes for traceability. They are dropped into shipping cartons or display cases, depending on the destination. These cartons are weighed, barcoded, and stacked automatically onto pallets. From there, the pallets move to temperature-controlled warehouses, where they await shipment to stores, vending distributors, movie theaters, and supermarkets. Throughout the factory, food safety is the top priority. Every step, from ingredient receiving to packaging, is conducted under good manufacturing practices. Workers wear protective clothing, hairnets, and gloves. Equipment is cleaned between production runs. Acid-resistant stainless steel and food-grade plastics are used throughout the facility. Environmental controls manage humidity and air filtration to ensure cleanroom-level hygiene in production zones. Sour Patch Kids production also involves detailed analytical testing. Random samples are pulled from each batch and tested in quality control labs for pH, moisture content, acid levels, color uniformity, texture, and shelf life stability. Sensory panels evaluate flavor consistency and sour-sweet balance. If any parameter is off, adjustments are made in the next batch, or the lot is held for investigation. As candy demand has grown, the process has become even more efficient through automation and smart technology. Modern factories use real-time data monitoring systems to control temperatures, mixer speeds, and depositor rates. Predictive maintenance software ensures machinery stays operational. Ingredient inventory is tracked digitally, and computerized dosing systems eliminate human error in weighing acids or colorants. Sustainability has also become a key consideration. Factories producing Sour Patch Kids increasingly aim to reduce water use, lower energy consumption, and source gelatin from suppliers who practice ethical sourcing. Even the packaging films are being redesigned in some regions to be recyclable or biodegradable. When the candy finally reaches store shelves, it has already traveled a long journey, from raw gelatin and sugar to the smiling, sour-coated figures we all recognize. Each bite delivers not only flavor, but the culmination of chemistry, engineering, and candy artistry. The sour then sweet experience isn't just a slogan. It's a precisely engineered sensory journey that begins with a sharp, puckering acid hit and fades smoothly into fruity, mellow sweetness. The process begins with the core ingredients: sugar, corn syrup, water, flavorings, and colorants. These are the building blocks of Jolly Ranchers, but the way they are combined and treated in the factory determines the final product's success. Sugar and corn syrup are delivered in bulk to the manufacturing plant, sugar often in powder or granulated form, and corn syrup as a thick liquid shipped in insulated tanker trucks to keep it warm and flowable. In the batching room, large stainless steel kettles are used to combine sugar, corn syrup, and a small amount of purified water. The goal is to dissolve the sugar and initiate a high-heat cooking process that transforms these ingredients into a highly concentrated, clear candy base. This cooking step is key. Jolly Ranchers are a type of hard candy, which means the sugar mixture must be cooked to what's known in confectionery as the hard crack stage, around 300 degrees to 310 degrees. These cooking kettles are jacketed with steam coils or electric heating elements that allow precise temperature control. As the mixture heats, the water begins to evaporate and the syrup thickens significantly. This evaporation is critical. It's what ultimately leaves the candy with such a low moisture content that it becomes glassy and brittle once cooled. Industrial stirrers keep the mixture agitated to ensure even cooking and prevent hot spots or scorching. As the syrup approaches the target temperature, automated sensors closely monitor the heat and viscosity. If the temperature is even slightly off, the final texture of the candy could be compromised. Undercooked syrup results in a sticky or chewy texture, while overcooked syrup becomes too brittle or may develop a burnt flavor. Once the sugar syrup reaches the perfect consistency, it's time to add the key components that give Jolly Ranchers their personality: flavor and color. The candy base is divided into smaller batches, each destined to become a different flavor: cherry, watermelon, green apple, blue raspberry, grape, and others. Each batch is transferred to flavoring tanks or mixing troughs where concentrated food-grade flavorings and dyes are added. These flavor compounds are highly concentrated and added in very specific ratios. Natural and artificial flavorings are used depending on the formulation. For example, a cherry Jolly Rancher might include benzaldehyde for that sharp, almond-like cherry punch, while green apple flavor could rely on malic acid esters for its tart kick. The colorants are also carefully chosen to match the expected visual identity of the flavor. Red 40, yellow 5, blue 1, and other FDA-approved synthetic dyes are often used in varying combinations to produce the vivid hues. Mixing must be fast and efficient at this stage because the candy syrup is still extremely hot and starts cooling quickly. Mixing arms or ribbon blenders integrate the flavor and color without introducing air bubbles, which would compromise the candy's clarity and structure. At this point, the flavored and colored syrup begins to thicken rapidly and takes on the consistency of hot, pliable taffy. Timing is critical. If it sets too quickly, it becomes unworkable. The next step is forming. Unlike many other candies that are molded in starch trays, Jolly Ranchers are formed using a process known as rope forming and die stamping. The hot candy is transferred onto cooling tables or through temperature-controlled rollers where it is shaped into thick, cylindrical ropes. These ropes are slowly cooled as they pass through stainless steel rollers and conveyors. The goal is to bring the candy down to a workable temperature where it can be cut and stamped, but not yet hardened completely. Once the candy ropes are at the right consistency, they pass through a forming machine fitted with precision dies. These dies stamp and cut the candy into individual pieces, each with the familiar oblong pillow shape. The forming machine applies enough pressure to ensure a clean cut, but not so much that it distorts the candy's surface. This is a delicate operation, as the candy is beginning to crystallize and solidify rapidly. The cutters must be kept heated or treated with food-safe lubricants to prevent sticking and preserve the clean edges of the final product. After forming, the individual Jolly Ranchers move on to a cooling conveyor system. These long, slowly moving belts expose the candies to progressively cooler ambient air or cooled forced air, gradually lowering their internal temperature. This slow cooling is important to prevent cracking and to ensure the surface remains glossy. If cooled too quickly, internal stresses could form, making the candy brittle or causing it to become cloudy. Once fully cooled and solid, the candies head to the wrapping stage. Each Jolly Rancher is immediately wrapped in a specially designed waxed film or polypropylene-based wrapper that prevents sticking and maintains freshness. Wrapping machines operate at extremely high speeds, feeding candies into synchronized rollers that twist wrap or fold seal each piece. The wrappers are pre-printed with branding, flavor indicators, and batch codes for traceability. The wrapped candies are then collected into large bins or counted into packaging units. Depending on the product line, Jolly Ranchers might be bagged into share-size pouches, fun-size treat bags, or bulk cartons. Form-fill-seal packaging equipment handles this part, weighing exact quantities of candies, dropping them into bags formed from a continuous roll of printed film, then sealing the bags with heat to make them tamper-evident and shelf-stable. As the candies are packaged, quality control plays a key role throughout the process. Random samples are taken and tested for color accuracy, size uniformity, hardness, and moisture content. Hardness tests may involve durometers or similar equipment that measures resistance to pressure, ensuring the candy has the right glass-like firmness. Flavor panels may also evaluate taste intensity, checking for flavor balance and clarity. If a batch is found to be off-spec, it may be rejected, reworked, or diverted to secondary markets. Behind all this precision lies rigorous food safety protocols. Workers wear gloves, hairnets, and lab coats in production areas. Machines are sanitized regularly, and allergen controls are in place even though Jolly Ranchers typically contain no nuts, dairy, or gluten. Hazard analysis and critical control point systems are used to identify and mitigate risks at each step of the process. From the moment the sugar is received to the point where a wrapped candy is sealed in a bag, every movement is monitored and recorded for traceability. Additionally, modern Jolly Rancher production facilities are incorporating automation and smart factory technologies. Recipe management systems ensure precise ingredient dosing, and digital controls allow managers to adjust batch temperatures and cooking times from central dashboards. Optical sensors inspect wrappers for misprints. Even the temperature and humidity of production rooms are computer controlled to maintain consistent output regardless of the season or climate outside. Sustainability is also being addressed in newer production lines. Energy-efficient kettles and heat recovery systems help reduce fuel use. Water used in equipment cleaning or steam generation is recycled where possible. Wrapping materials are being developed with recyclability in mind, and many facilities are exploring biodegradable or compostable film options. The finished Jolly Ranchers, now bagged and boxed, are stacked onto pallets and moved into climate-controlled warehouses for distribution. These candies are remarkably stable, with long shelf lives due to their low moisture content and protective wrapping. This makes them ideal for global shipping. From there, they head to supermarkets, convenience stores, vending machines, and movie theaters all around the world, ready to deliver that unmistakable burst of sour cherry, green apple, or blue raspberry flavor. It all begins with the selection and preparation of the raw ingredients. At the core of every Haribo gummy candy is a combination of sugar, glucose syrup, gelatin, citric acid, fruit flavoring, and food coloring. These ingredients must be carefully sourced and managed to ensure the consistent taste, texture, and appearance that consumers expect. Sugar and glucose syrup form the base of the gummy. These are typically delivered to the Haribo factory in large quantities, sugar in bulk containers or silos, and glucose syrup in insulated tankers to maintain fluidity. In the production facility, the sugar and glucose syrup are fed into large stainless steel kettles equipped with steam jackets and stirring paddles. The mixture is gently heated and stirred to fully dissolve the sugar crystals, creating a thick, sweet solution. This sugary base is the fundamental building block for all Haribo products. Once the sugar solution reaches the appropriate concentration and temperature, gelatin is introduced. Gelatin is a key functional ingredient in Haribo gummies, providing their characteristic chewiness and structure. It is typically derived from pork or beef collagen and arrives at the factory in dehydrated granule or sheet form. Before it can be added to the sugar mixture, the gelatin is first hydrated in warm water in separate mixing tanks. Once fully dissolved, the gelatin is combined with the hot sugar syrup under controlled conditions. The resulting mixture is carefully heated to a precise temperature, usually around 150 to 160 degrees, ensuring full integration of the gelatin without degrading its gelling ability. During this step, any acids such as citric acid or malic acid are also added. These acids are responsible for the pleasant tang that balances the sweetness of the candy and enhances the fruit flavors. Next, the flavorings and colors are introduced. Haribo uses a range of natural and artificial fruit flavors to create its signature gummy taste profiles. Each flavor, lemon, orange, raspberry, pineapple, and apple, among others, is blended in concentrated liquid form and carefully metered into separate batches of the hot candy mix. Food-grade colorants are added alongside the flavorings, giving each candy its bright, transparent hue. The combination of flavor and color must be exact to meet Haribo's internal standards, and flavor technicians often perform sensory evaluations during production. With the flavored and colored syrup fully prepared, it is ready for the molding process. Haribo gummies are formed using a traditional confectionery technique known as starch molding, or the starch mogul system. This process begins with large trays filled with cornstarch. A molding board presses bear-shaped cavities into the surface of the starch, creating hundreds of individual molds per tray. The hot, viscous candy mixture is poured into these molds using automated depositors equipped with multiple nozzles. Each nozzle dispenses the exact volume of syrup needed to fill a single bare cavity, ensuring uniform size and weight across thousands of pieces. The trays are then stacked and transferred to a curing room, a warm, dry environment where the candies are allowed to set for 24 to 48 hours. During this curing period, the gelatin network solidifies, giving each gummy its final elastic texture. The starch not only supports the shape, but also absorbs moisture from the surface of the candy, helping to achieve the perfect skin. Once the gummies are fully cured, the trays are sent to a destarching machine. This piece of equipment gently tumbles the trays, separating the candy pieces from the cornstarch. Vibrating screens and air jets remove any excess starch, which is collected, filtered, and reused in the molding process. The newly formed gummies, now free of starch and fully set, are inspected and prepared for the next stage. Now comes the coating process, which adds shine and improves handling. Haribo gummies are typically coated with a thin layer of food-grade wax, such as carnauba wax or beeswax, and vegetable oil. This coating is applied in rotating drums or tumblers, where large quantities of gummies are gently mixed while a light mist of the wax solution is sprayed over them. The result is a glossy surface that prevents the candies from sticking together and enhances their visual appeal. The wax also serves as a moisture barrier, helping to preserve the candy's freshness during storage and transport. After coating, the gummies pass through a final inspection phase. This includes both visual inspections by trained staff and automated optical systems that check for shape uniformity, color consistency, and size accuracy. Any defective or malformed candies are removed from the line and discarded or recycled, depending on the facility's protocols. Next, the candies move on to the packaging line. Haribo uses a range of packaging formats, including peg bags, share-size pouches, single-serve packs, and multi-flavor assortments. The packaging process begins with high-speed form-fill-seal machines. Printed plastic film is unrolled and shaped into pouches, which are then filled with a precise weight of gummies. The bags are sealed using heated jaws that bond the plastic layers together, creating an airtight, tamper-evident package. The filled bags are then printed with production information such as batch number, expiration date, and sometimes promotional codes or QR codes for consumer engagement. They are packed into cartons, stacked onto pallets, and moved to the warehouse where they await distribution. Throughout this final stage, quality control teams monitor the sealing integrity, fill weights, and print accuracy to ensure compliance with product specifications. Behind the scenes, every Haribo production facility operates under strict food safety and quality assurance protocols. These include adherence to good manufacturing practices, hazard analysis and critical control points, and ISO quality standards. Production areas are cleaned regularly, equipment is sanitized, and every batch is traceable from raw ingredient to finished product. Samples are pulled at every stage and tested in on-site laboratories for pH, moisture content, texture, and microbial safety. Modern Haribo factories also make use of advanced automation and data analytics. Ingredient dosing is controlled by programmable logic controllers to reduce human error. Sensors monitor cooking temperatures, gelatin concentration, depositor output, and humidity levels in real time. Production managers can access digital dashboards to track performance metrics and respond quickly to any deviations. These innovations not only improve efficiency, but also support the consistency that Haribo is known for. As a global brand, Haribo also customizes its recipes and flavors for different regions. For example, gummies produced in Europe may use natural colorings derived from fruit and vegetable concentrates, while US products may include certified synthetic dyes. Flavors may also vary to suit local preferences, such as blackcurrant in the UK, mango in Asia, or sour varieties in North America. Despite these differences, the core manufacturing process remains largely the same across all Haribo facilities. Sustainability is another growing focus in Haribo's operations. The company has been investing in renewable energy, water conservation, and waste reduction across its factories. Ingredient sourcing increasingly considers environmental impact and animal welfare, particularly in the sourcing of gelatin. Packaging materials are being re-evaluated to include recyclable films and reduce plastic usage. When a bag of Haribo Gold Bears finally lands on store shelves, it represents a highly coordinated blend of traditional candy-making techniques and modern industrial precision. Each chewy bear is the product of strict formulation, controlled cooking, precise molding, and sophisticated quality checks. From sugar kettle to glossy, colorful treat, the journey of a Haribo gummy is a testament to the art and science of confectionery manufacturing. While the candies may be playful and whimsical, the process behind them is anything but casual. It requires the coordination of food engineers, quality control experts, maintenance technicians, flavor developers, and packaging specialists, all working together to ensure that every handful of Haribo delivers the same beloved taste and texture, whether it's made in Germany, the United States, or anywhere else Haribo operates. This level of consistency and care is what has allowed the brand to thrive for over a century, making Haribo gummies a global favorite that continues to delight generation after generation.